Good evening and welcome to Physic for Sleep. Tonight we embark on an intellectual journey exploring one of the universe's most ubiquitous and fascinating phenomena. Why everything, from the smallest dust motes to the grandest galaxies, seems to be in a constant state of spin. Before we gently immerse ourselves in the cosmic waltz of rotation, I would like to know where you are at this moment. Perhaps you are nestled in your favorite reading nook, the pages of a forgotten book resting on your chest, or maybe you are gazing out a window, watching the silent dance of snowflakes under a street lamp. If these deep reflections help you relax and organize your thoughts before sleep, please support the channel with a like and subscribe so others can find their way here too. Now, just breathe, allow your eyes to grow heavy, and let's begin. The universe, in its boundless expanse, reveals a profound affinity for rotation. From the delicate swirl of a nascent star system to the majestic spiral arms of distant galaxies, spin appears to be an almost universal constant, a fundamental rhythm woven into the very fabric of existence. But why is this so? What cosmic principle orchestrates this ceaseless dance, ensuring that almost everything we observe is in a state of perpetual turn? The answer lies in one of the most elegant and far-reaching laws of physics, the conservation of angular momentum. Imagine, if you will, a figure skater gracefully gliding across the ice. As she begins her spin, her arms are outstretched, slowing her rotation. Yet, as she draws her arms inward, closer to her body, her rate of spin dramatically increases. She hasn't exerted any additional force. She has simply redistributed her mass. This everyday observation beautifully illustrates the principle at play. Angular momentum, a measure of an object's tendency to continue rotating, depends on three primary factors: the object's mass, how that mass is distributed relative to its axis of rotation, and its rotational velocity. The law of conservation of angular momentum states that, in an isolated system, this total quantity remains constant. If the mass distribution changes, the rotational speed must adjust accordingly to maintain equilibrium, a delicate balance ceaselessly at work across all scales of the cosmos. Now, let us apply this quiet yet powerful law to the grand canvas of the cosmos. Consider the birth of a star, or indeed an entire solar system like our own. It begins as an immense diffuse cloud of gas and dust, perhaps many light years across, floating silently in the vast interstellar medium. This cloud, though seemingly still to our eyes, is never perfectly motionless. It possesses an almost imperceptible, slight rotation, a gentle inherent swirl imparted by the turbulent motions of the gas within, or by gravitational interactions with other nearby celestial bodies. As gravity, the tireless architect of the universe, begins to pull this vast cloud inward, causing it to collapse upon itself, its overall size dramatically decreases. Much like our ice skater drawing in her arms, the mass of the cloud is now concentrated ever closer to its central axis. To conserve its angular momentum, this collapsing cloud must, by necessity, spin faster, transforming its slow initial drift into a more pronounced rotation. This accelerated rotation is not merely a curiosity. It is a critical process that shapes the very structures we see forming around us. As the cloud spins more rapidly, centrifugal forces push material outward, resisting further collapse along the rotational axis. This causes the cloud to flatten into a distinct, rotating disk, often called a protoplanetary disk, with a dense, rapidly spinning core at its very heart. This core, continuing to gather mass and contract under immense gravitational pressure, eventually ignites into a protostar, the embryonic stage of a new sun. The remaining material in the flattened disk continues to swirl, gently colliding and clumping together under its own localized gravity to form planetesimals, which then coalesce into larger planets, asteroids, and other celestial bodies. All these newly formed objects inherit this rotational motion, orbiting and rotating in the same general direction as their parent star. Thus, the spin of a planet, including our own Earth, and its graceful orbit around the Sun are direct consequences of the initial, almost negligible rotation of a primordial gas cloud, amplified over millions of years by the immutable laws of physics. This same elegant principle extends profoundly to the formation of galaxies themselves. Modern cosmological models, robustly supported by extensive astronomical observations, suggest that galaxies begin as vast, slightly overdense regions in the early universe, composed primarily of enigmatic dark matter and the most fundamental elements, primordial hydrogen and helium gas. These immense proto-galactic structures, too, possess tiny initial rotational components, subtle eddies in the cosmic flow. As gravity draws this colossal amount of matter inward over billions of years, the system collapses dramatically. And just as with a star-forming cloud, this monumental gravitational collapse, combined with the unwavering conservation of angular momentum, causes the material to spin faster and flatten into the magnificent spiral or disk shapes characteristic of many galaxies. The countless stars within these galaxies, including our own Sun, then orbit the galactic center, creating the breathtaking cosmic whirlpools we observe through our powerful telescopes. Even elliptical galaxies, which appear less organized and more spheroid in shape, still possess significant internal motion and rotation, though their formation pathways might involve mergers that redistribute angular momentum in different yet equally governed ways. The profound beauty of this pervasive rotation is that it clearly demonstrates how fundamental physical laws govern phenomena across truly vast scales, from the subatomic realm to the largest structures in the observable universe. It is a constant reminder that even the most complex and awe-inspiring cosmic events can often be traced back to relatively simple, elegant principles. Our very existence on a spinning planet orbiting a spinning star within a spinning galaxy is a testament to this inherent rotational tendency. It means that the universe is not static, not inert, but a dynamic, swirling entity, always in motion, always responding to the conserved quantities that dictate its grand evolution. This continuous, quiet hum of angular momentum, constantly at work, sculpts the cosmos into the familiar, yet endlessly wondrous, rotating structures that fill our night sky, providing a stable, predictable motion for our celestial home. And when we consider this cosmic ballet, this universal spin that pervades everything, it offers a gentle invitation to pause and reflect on our own place within it. We are not merely observers, but active participants, living on a world that is itself a product of this ceaseless rotation. Our days and nights, our seasons, even the very forces that shaped our planet into a habitable sphere, are all intricately linked to the conservation of angular momentum. It is a silent, invisible force, yet it defines the very rhythm of our cosmic home, offering a profound sense of interconnectedness with the swirling grandeur of the universe, a very lullaby of rotational physics. The conservation of angular momentum, while a foundational explanation for the initial spin of celestial bodies, is not the sole orchestrator of their intricate rotational dances. Once these spinning structures are formed, a complex interplay of forces, particularly gravitational and tidal interactions, further refines and alters their individual rotations, creating the diverse array of spins we observe throughout the cosmos. Consider, for instance, the subtle yet significant effect of a planet's rotation on its own shape. As a celestial body spins, the centrifugal force, which pushes matter outward from the axis of rotation, causes it to bulge slightly at its equator and flatten at its poles. This phenomenon, known as oblateness, is particularly noticeable in rapidly rotating gas giants like Jupiter and Saturn, whose equatorial diameters are significantly larger than their polar diameters. For Saturn, this difference can be as much as 10%, a visible flattening that speaks volumes about its rapid internal motion. Even our own Earth, though seemingly a perfect sphere, is not entirely so. Its equatorial bulge is a measurable effect of its daily rotation. This subtle distortion is a constant, gentle reshaping, a testament to the dynamic relationship between a body's internal mass distribution and its angular velocity, a silent, ongoing dialogue between mass and motion. It reminds us that even seemingly solid worlds are not rigid, but rather fluid entities, subtly responding to the forces of their own motion. Beyond self-shaping, the gravitational embrace between celestial partners can also dramatically influence their spins. This is where tidal forces enter the cosmic narrative. Imagine our Earth and its faithful companion, the Moon. The Moon's gravity exerts a pull on Earth, but this pull is not uniform across our planet. The side of Earth facing the Moon experiences a stronger gravitational tug than the side furthest away, creating a slight stretching effect. This differential gravitational force is what we call a tidal force, and it manifests most visibly in our ocean tides, pulling the vast waters of our world into rhythmic swells. However, these forces also act on the solid body of the Earth, creating a subtle bulge of rock and land. As Earth rotates beneath these bulges, the Moon's gravity attempts to pull them back into alignment, effectively creating a gentle, persistent break on Earth's rotation. Over immense spans of geological time, this tidal friction has been steadily slowing Earth's spin, leading to longer days. In return, this transfer of angular momentum causes the Moon to slowly spiral outward, moving approximately 3.8 centimeters away from Earth each year. This dance of tidal locking is a common theme across the solar system and beyond. Many moons, including our own, are tidally locked with their parent planets, meaning their rotation period precisely matches their orbital period. The result is that they always present the same face to the planet they orbit, a phenomenon that offers a profound stillness when observed from the planet's surface. Pluto and its largest moon, Charon, offer an even more intricate example, being mutually tidally locked, each forever presenting the same face to the other, locked in an eternal silent gaze, a perfect gravitational dance of two celestial partners. Such synchronized rotation is not an accident, but the inevitable outcome of billions of years of gravitational interaction, a testament to the slow, relentless power of tidal forces to redistribute angular momentum until a state of stable equilibrium is reached. Furthermore, the grand spectacle of galactic collisions and mergers provides another powerful illustration of how angular momentum is redistributed on truly colossal scales. Galaxies are not isolated islands in space. They frequently interact, gravitationally influencing and occasionally merging with one another. When two spiral galaxies, each with its own immense store of angular momentum, slowly drift together and begin to merge, the outcome is often a dramatic reshaping. The individual spins and orbital motions of billions of stars, gas clouds, and dark matter particles are violently reconfigured. The original disk structures can be disrupted, leading to bursts of star formation as gas clouds collide and compress, and the overall angular momentum of the system is conserved but redistributed. The resulting merged galaxy, often an elliptical galaxy, may have a different, less organized, but still very real pattern of internal rotation, an ancient echo of its tumultuous past. These cosmic collisions are not destructive in a final sense, but rather transformative, facilitating a grand reorchestration of matter and energy where the total angular momentum of the system persists, even as its individual components are profoundly altered. And then we arrive at the most extreme manifestations of rotation, the spinning leviathans of the universe, black holes. These enigmatic objects, born from the collapse of massive stars, can retain an immense amount of angular momentum from their progenitors. A spinning black hole, known as a Kerr black hole, possesses a rotational energy so vast that it literally drags space-time around it, bending the very grid of existence. This phenomenon is called frame dragging or the Lenz-Thirring effect, a direct prediction of Albert Einstein's general theory of relativity. Imagine space and time not as a static backdrop, but as a viscous fluid. A spinning black hole acts like a giant rotating spoon stirring this fluid, causing space-time itself to swirl in its vicinity. Any object passing close to a spinning black hole, even if it tries to remain stationary, will find itself irresistibly pulled along by the rotating fabric of space-time. This means that near a spinning black hole there is a region, the ergosphere, where it is impossible to stand still. One must move with the flow of space-time, like being caught in a powerful cosmic current. It is a profound testament to the power of rotation, not just to move matter, but to twist the very stage upon which the cosmic drama unfolds, a phenomenon that truly stretches the imagination. In considering these varied expressions of rotation, from the subtle bulge of a planet to the space-time twisting dance of a black hole, we are gently reminded that the universe is a place of ceaseless, dynamic activity. The spin is not just an incidental feature, it is an active participant in the ongoing evolution of everything. It shapes worlds, dictates the long-term fates of moons, and dramatically reconfigures entire galaxies. It even reveals the most profound and exotic predictions of our theories of gravity. And as we contemplate these immense rotational forces, we might find a quiet comfort in the knowledge that our own small world, our very existence, is part of this grand, ceaselessly turning cosmic mechanism. We are, in a very real sense, spinning through space, carried by these ancient, immutable laws, a part of the universe's unending rotational symphony. While we have explored the grand, macroscopic ballet of celestial bodies, it is worth pausing to consider that the phenomenon of spin reaches even deeper, into the very heart of matter itself, into the quantum realm. Here, particles, the fundamental constituents of everything we perceive, possess an intrinsic property known as spin. This is not the classical rotation of a tiny sphere, for quantum particles are often considered point-like, without discernible parts to physically rotate. Instead, quantum spin is a purely quantum mechanical angular momentum, a fundamental characteristic akin to mass or electric charge. It dictates how particles interact with magnetic fields and with each other, profoundly influencing the structure of atoms and the very stability of matter. First conceptualized in the 1920s by physicists like George Uhlenbeck and Samuel Goudsmit, and later rigorously embedded in Paul Dirac's relativistic quantum mechanics, spin is an inherent, unchangeable property, an internal compass for the universe's smallest components. This intrinsic spin, often visualized metaphorically as an arrow pointing in a particular direction, comes in discrete values. Electrons, for example, are said to have a spin of 1/2, meaning they can exist in one of two states: spin up or spin down. This seemingly abstract property has immense consequences, far beyond the confines of theoretical physics. It is, for instance, a crucial component of the Pauli exclusion principle, a cornerstone of quantum mechanics, which states that no two identical electrons can occupy the same quantum state simultaneously. This principle is not just a theoretical curiosity. It is the fundamental reason why atoms have distinct electron shells, why elements possess unique chemical properties that allow for the vast diversity of molecules, and ultimately, why solid matter exists at all. Without quantum spin and the Pauli exclusion principle, electrons would simply collapse into the lowest energy state, and the universe as we know it would be a formless, featureless soup, devoid of structure or complexity. This quantum spin even forms the very foundation of emerging technologies like quantum computing, where these spin-up and spin-down states, unlike classical bits that are either 0 or 1, allow for superposition and entanglement, holding the promise of revolutionary computational power. So, even within the stillness of our own bodies, a ceaseless quantum spin is at play, a silent, intricate dance underpinning all physical reality, keeping us from falling through the floor and allowing our very atoms to maintain integrity. Moving back to larger, yet still deeply connected scales, the rotation of massive celestial bodies often intertwines profoundly with another fundamental force: magnetism. Many planets, like our Earth, and certainly all stars, generate powerful magnetic fields through a self-sustaining process known as the dynamo effect. This complex phenomenon occurs when a large body of electrically conductive fluid, such as Earth's churning, molten iron outer core or the Sun's vast convective plasma, undergoes differential rotation and turbulent motion. The intricate fluid dynamics, rapid rotation, and presence of free electrical charges within these layers create powerful currents, which in turn generate magnetic fields that amplify and sustain themselves in a continuous feedback loop. For Earth, this powerful geomagnetic field extends far into space, creating a protective bubble called the magnetosphere, a vital shield that deflects harmful charged particles from the solar wind and cosmic radiation, making life on the surface possible by preventing atmospheric erosion. This quiet guardian, born from the very act of Earth's internal spin, is a constant, unseen presence, a testament to the dynamic interplay between motion and fundamental forces within our planet's deep interior. Similarly, the dynamo effect, which we briefly touched upon in our previous reflections, is a mesmerizing testament to the intricate link between a celestial body's rotation and its magnetic fields. Within the heart of our own Sun, this mechanism is at work on a truly colossal scale, generating a magnetic field that extends throughout our entire solar system. The Sun, a vast sphere of superheated plasma, does not rotate as a solid body. Instead, it exhibits what scientists call differential rotation. Its equator spins faster than its poles. This uneven rotation, coupled with the convection currents that constantly churn and flow within its plasma, twists and stretches the magnetic field lines. Imagine these lines as elastic bands being stretched and tangled by the Sun's internal movements. This continuous stretching and tangling leads to a periodic buildup of magnetic energy, which can manifest dramatically as sunspots, solar flares, and coronal mass ejections. These powerful events release immense amounts of energy and charged particles into space, forming the solar wind that constantly washes over our planetary system. This solar wind, a stream of energetic particles, interacts with the magnetic fields and atmospheres of planets, including Earth. While our planet's magnetosphere largely protects us, these interactions can still have subtle effects, influencing everything from auroras dancing in the polar skies to the gradual erosion of planetary atmospheres over eons. The Sun's rotation, therefore, is not merely an internal characteristic. It is a dynamic force that actively shapes the environment within which our planets evolve, a constant, gentle breath of stellar energy influencing the very air we breathe. It is a profound illustration of how the spin of one celestial giant can ripple outwards, touching the farthest reaches of its dominion and influencing the rotational evolution of its smaller companions. But if the Sun's rotation is a grand and powerful engine, consider the extreme, almost unbelievable, spins found in the remnants of once massive stars. When a star far more massive than our Sun exhausts its nuclear fuel and undergoes a spectacular supernova explosion, its core collapses inward with unimaginable force. If this collapsing core is not massive enough to form a black hole, it can become a neutron star, an object so dense that a single teaspoon of its material would outweigh Mount Everest. These neutron stars are typically only about 20 kilometers in diameter, roughly the size of a city, yet they contain more mass than our entire Sun. And crucially, they spin with astonishing rapidity. The initial angular momentum of the larger, slowly rotating star is conserved during this extreme collapse, much like our figure skater pulling in her arms, but to an infinitely greater degree. The result is a neutron star that can spin hundreds, even thousands, of times per second. Many of these rapidly spinning neutron stars are observed as pulsars, cosmic lighthouses that emit focused beams of radio waves from their magnetic poles. As the neutron star rotates, these beams sweep across space, and if one of them happens to cross our line of sight here on Earth, we detect a precise, rhythmic pulse. The regularity of these pulses is so extraordinary that pulsars are among the most accurate clocks known in the universe, more stable than even the atomic clocks we use on Earth. This precise, relentless spin, born from the violent death of a star, offers us an unparalleled tool for probing the fundamental properties of space-time and the extreme physics of the universe. Some neutron stars, known as magnetaires, combine this incredible spin with magnetic fields that are 1,000 trillion times stronger than Earth's, fields so powerful they can distort atoms and even rip apart distant objects with their sheer magnetic force. These objects are truly monuments to the power of rotation in its most extreme cosmic forms. Bringing our focus back to our own planetary home, the Earth's rotation also sculpts the dynamics of its atmosphere and oceans in ways that profoundly affect our daily lives. The Coriolis effect, named after the French mathematician Gaspard Gustave Coriolis, is a fascinating manifestation of this planetary spin. It describes the apparent force that deflects moving objects, including air and water currents, on a rotating frame of reference. On Earth, this means that air currents and ocean currents are deflected to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection is not a true force in the Newtonian sense, but rather an inertial effect arising from our perspective on a spinning planet. The Coriolis effect is responsible for the large-scale patterns of global wind systems, such as the trade winds and the westerlies, which are crucial for distributing heat and moisture around the globe. It also plays a pivotal role in the formation of weather phenomena, like hurricanes and cyclones, causing them to spin in characteristic directions, counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. Similarly, vast ocean currents, those silent rivers within the seas, are shaped and guided by this same rotational influence, transporting warm and cold waters across continents and profoundly impacting regional climates. So, while we may not consciously perceive Earth's rotation in our everyday moments, its effects are woven into the very fabric of our weather, our climate, and the natural world around us. It is a subtle, yet omnipresent reminder that we live on a spinning world, where every gust of wind and every ocean wave is part of a grand planetary ballet orchestrated by the laws of rotation. And as we consider these various manifestations of spin, from the quantum dance of electrons to the sun's magnetic breath, to the extreme rotations of pulsars and the shaping of our own planet's weather, we are invited to see the universe not as a static collection of objects, but as a vibrant, dynamic system where motion is fundamental. Each spin, each orbit, each tidal interaction is a thread in the cosmic tapestry, weaving together the past, present, and future of everything. Our understanding of this universal rotation allows us to perceive a deeper order, a quiet harmony in the ceaseless turning of the cosmos, a profound rhythm that extends from the smallest particle to the grandest galaxy, influencing our very existence in ways both subtle and truly profound. The rhythmic turning of worlds and stars, this cosmic symphony of spin, has implications that stretch far beyond the mere distribution of angular momentum or the shaping of planetary bulges. Indeed, the very capacity of a planet to foster and sustain life is often intricately tied to its rotation, particularly through the generation of a protective magnetic field. As we discussed, the dynamo effect, driven by the rapid differential rotation of a planet's electrically conductive liquid core, creates a powerful magnetosphere. For Earth, this invisible shield is an indispensable guardian, deflecting the relentless barrage of charged particles emanating from our Sun, known as the solar wind. Without this magnetic bubble, these high-energy particles would steadily strip away our atmosphere, much like a gentle, persistent breeze eroding a sand dune, making the surface uninhabitable and exposing any nascent life to harmful radiation. Consider the stark contrast offered by our celestial neighbor, Mars. Billions of years ago, Mars was a warmer, wetter world, likely possessing a denser atmosphere and even liquid water on its surface. Scientists believe that as this smaller planet cooled more rapidly than Earth, its molten core solidified, or at least its convection currents ceased to be sufficiently vigorous. Consequently, the dynamo effect weakened and eventually shut down. The loss of its global magnetic field left Mars's atmosphere utterly vulnerable to the solar wind. Over geological timescales, this relentless bombardment slowly but inexorably eroded away much of its atmospheric gases, transforming a once potentially clement world into the cold, arid, and thinly veiled desert we observe today. This quiet ancient catastrophe underscores the profound importance of a planet's internal spin in shaping its long-term habitability and its capacity for fostering complex life. Venus, another neighbor, presents a different scenario, with its extremely slow rotation contributing to its lack of a strong global magnetic field, leaving it exposed and leading to a runaway greenhouse effect that created its scorching, dense atmosphere. These planetary tales whisper a consistent truth. Spin is not just about motion. It is about protection, about the very conditions that allow life to flourish and endure. Beyond these broad planetary effects, the subtle dance of gravity and rotation can lead to even more nuanced and stable configurations known as spin-orbit resonances. We previously touched upon tidal locking, where a moon's rotation period matches its orbital period, always showing the same face to its parent. But some celestial bodies exhibit more complex, yet equally stable, synchronized rhythms. Mercury, for instance, once thought to be tidally locked in a one-to-one resonance with the Sun, actually rotates exactly 3 times on its axis for every 2 orbits it completes around our star. This 3-to-2 spin-orbit resonance is a stable outcome of the interplay between the Sun's powerful tidal forces and Mercury's significantly elliptical orbit. At its closest approach to the Sun, the tidal forces are strongest, subtly tugging at Mercury's slightly elongated shape. Over immense spans of time, these repeated tugs, synchronized with its orbital motion, nudged Mercury into this stable, resonant state. It is a testament to the universe's capacity for creating intricate, self-sustaining patterns, a cosmic clockwork that appears far more complex than simple synchronicity. This principle of resonance extends elegantly to multiple body systems, especially evident among the moons of the gas giants. Jupiter's 3 innermost Galilean moons, Io, Europa, and Ganymede, are locked in a captivating orbital resonance known as the Laplace resonance. For every 4 orbits of Io around Jupiter, Europa completes exactly 2 orbits, and Ganymede completes precisely 1. This gravitational synchronicity, while primarily governing their orbital periods, has profound implications for their internal dynamics and, by extension, their rotational states. The constant rhythmic gravitational tug-of-war between these moons, coupled with Jupiter's immense gravity, creates a powerful kneading effect within their interiors. This continuous flexing generates immense tidal heating, particularly pronounced in Io, making it the most remarkably volcanically active body in our entire solar system. Its very geological dynamism, its molten heart, and its ceaseless eruptions are a direct consequence of this resonant orbital dance, a grand demonstration of how subtle gravitational whispers between celestial bodies can unleash immense internal energies, even shaping their rotational characteristics and influencing their potential for subsurface oceans, as theorized for Europa. The delicate balance between gravity and the centrifugal force generated by rotation is also crucial for the structural integrity and stability of larger cosmic entities, preventing them from succumbing to collapse. Consider the vast, swirling disks of spiral galaxies like our own Milky Way. The stars, gas, and dust within these galaxies are not simply falling towards the supermassive black hole at the center. Their orbital motion, their collective spin, provides the necessary centrifugal support to counterbalance the immense gravitational pull of the galactic core and the surrounding dark matter halo. Without this rotation, these grand structures would simply collapse into more compact, spherical forms. This rotational stability is a fundamental aspect of galactic morphology, determining why some galaxies are flat, spinning disks, while others are more diffuse, elliptical shapes with less coherent rotation. It is a dynamic equilibrium, a cosmic balancing act that allows these magnificent stellar islands to maintain their form and continue their slow, majestic dance across billions of years. Furthermore, the very stability of individual stars is predicated on a similar balance. The outward pressure generated by nuclear fusion in their cores counteracts the inward pull of gravity, but their rotation also contributes to their overall shape and stability, especially for rapidly spinning stars. For some massive, rapidly rotating stars, the centrifugal force at their equator can become so strong that it almost equals the gravitational pull, causing them to bulge dramatically and even shed material into space. This phenomenon, observed in some B-type stars, demonstrates the extreme limits of rotation, where the very integrity of a star can be challenged by its own spin. This delicate interplay, this constant tension between the inward crush of gravity and the outward push of rotational forces, is a universal theme, shaping the very existence and evolution of everything from the smallest moon to the grandest galaxy. It is a profound realization that the universe is not merely filled with objects, but with objects in constant, purposeful motion, each spin a story of cosmic forces in elegant, ceaseless interaction. And as we drift further into the quietude of the night, letting these cosmic rotations fill our thoughts, we can find a sense of profound belonging. Our spinning Earth, our life-giving Sun, and the distant swirling galaxies all are bound by these same elegant laws of motion. This deep universal rhythm reminds us that we are not separate from the cosmos, but intimately connected to its grand rotational ballet, a part of its silent, enduring dance, leading us gently into deeper contemplation. The Sun's magnetic breath, as we considered, is a magnificent outcome of its internal rotation, a force that shapes the very environment of our solar system. Yet, to truly understand the ubiquity of spin, we must cast our minds back even further, to the very genesis of the universe itself. How did this primordial rotation, these subtle initial swirls that would eventually coalesce into galaxies and stars, first arise? Scientists believe that the very early universe, though largely uniform, was not entirely devoid of minuscule irregularities. These tiny anisotropies, small deviations from perfect smoothness, may have originated from quantum fluctuations during the inflationary epoch, that incredibly brief period just after the Big Bang when space expanded exponentially. While these fluctuations were initially on subatomic scales, inflation stretched them to cosmic proportions, seeding the universe with slight overdensities and underdensities of matter and energy. It is within these nascent cosmic structures that the seeds of rotation were likely sown. As these slightly denser regions began to gravitationally attract more matter, they also started to collapse. Any infinitesimal initial angular momentum present within these vast turbulent primordial gas clouds would have been amplified, much like our earlier example of the ice skater, but on a scale that defies easy comprehension. Gravitational instabilities, coupled with the conservation of angular momentum, would have caused these proto-galactic clouds to slowly begin their majestic inward spiral, gradually flattening and accelerating their spin over billions of years. This process, often referred to as cosmic turbulence or the amplification of initial vorticity, suggests that the universe's inherent tendency to spin is a direct, inescapable consequence of its very birth and subsequent evolution, a deep-seated characteristic rather than a mere coincidence. It means that the rotational motion we observe in galaxies today is an ancient echo, a lingering memory of the universe's earliest moments, woven into the fabric of its emergent structure. This dynamic interplay of gravity and rotation finds perhaps its most dramatic expression in the phenomena of accretion disks. These are not merely passive collections of matter, they are celestial engines, where gas and dust swirl rapidly around a central massive object. be it a young protostar, a white dwarf, a neutron star, or most spectacularly, a supermassive black hole. For matter to fall onto such a central object, it must shed its angular momentum. Without a mechanism to do so, it would simply orbit forever, never reaching the gravitational embrace of the core. The accretion disk itself provides this ingenious solution. Particles within the disk experience internal friction and turbulence akin to a cosmic viscosity. This friction causes some material to lose angular momentum and spiral inward, while other material gains angular momentum and drifts outward. As matter spirals inward, it accelerates to incredible speeds, heating up to millions of degrees through friction and compression. This superheated plasma then emits vast amounts of radiation across the electromagnetic spectrum, making accretion disks some of the brightest and most energetic objects in the universe. The energy released by matter spiraling into a black hole can be far more efficient at converting mass into energy than nuclear fusion in stars. It is a process of controlled rotational decay, where the shedding of spin transforms gravitational potential energy into light and heat, allowing us to observe these otherwise invisible cosmic behemoths from light years away. This rotational mechanism is not just about feeding a black hole. It is fundamental to the very process of star formation, where protostellar disks similarly funnel material onto a growing star, demonstrating its pervasive influence. The extreme rotation within these accretion disks also plays a crucial role in the creation of another awe-inspiring cosmic phenomenon: astrophysical jets. Many actively accreting black holes and young protostars are observed to launch incredibly powerful, collimated beams of plasma at nearly the speed of light, extending thousands, even millions of light years into space. These jets are thought to be generated by a complex interplay of the rapidly spinning accretion disk and strong magnetic fields. The magnetic field lines anchored in the rotating disk and perhaps twisted by the central object itself act like a cosmic slingshot or a powerful nozzle. As plasma from the inner regions of the disk is caught up in these twisted magnetic fields, it is accelerated and channeled outward along the rotational axis, forming these spectacular jets. This mechanism, while still an active area of research, clearly demonstrates how the energy of rotation, combined with magnetic forces, can be harnessed and directed into powerful outflows. These jets are not just beautiful, they are significant cosmic architects. They can influence star formation in galaxies by sweeping away gas clouds, and they can transport energy and heavy elements far into the intergalactic medium. Thus, the spin of a black hole and its surrounding accretion disk is not merely a local curiosity. It is a driving force that shapes the evolution of entire galaxies and the distribution of matter across the largest cosmic scales. It is a profound yet tranquil reminder that even the most violent-seeming processes in the universe are often manifestations of fundamental physical laws, playing out with a majestic, inevitable grace. Finally, we might gently ponder the ultimate fate of this universal spin. Will everything continue to rotate indefinitely? While the conservation of angular momentum is a powerful law, systems are rarely perfectly isolated. Over immense stretches of cosmic time, various subtle forces can act to dissipate or transfer rotational energy. Gravitational waves, ripples in space-time predicted by Einstein, and recently observed from merging black holes and neutron stars, carry away angular momentum from orbiting systems. Small frictional forces within gas clouds, or the slow, persistent tug of tidal interactions, can also gradually alter spins. However, for most large, isolated celestial bodies and systems, their rotation is incredibly stable and persistent over timescales that dwarf human comprehension. Galaxies will continue their grand spiral for trillions of years, and planets will spin for eons unless perturbed by catastrophic collisions or the slow, inexorable cooling of their cores. The universe, in its deep wisdom, seems designed for enduring motion. And as we conclude this exploration of cosmic spin, From its quantum origins to its galactic expressions, we realize that rotation is not just a scientific concept, but a profound aspect of the universe's character. It is the silent engine of creation, the sculptor of planets, the protector of life, and the source of some of the most energetic phenomena we know. To understand why everything spins is to grasp a deeper layer of the universe's elegant machinery, a quiet, persistent hum that resonates through all of existence. It is a calming thought, isn't it, to know that we are a tiny conscious point within a universe that spins with purpose and enduring grace. A ceaseless turning that shapes everything from the smallest particles to the grandest galaxies. Yet this universal spin is not merely a local phenomenon confined to individual celestial bodies or their immediate systems. Recent observational data, gathered through meticulous surveys of the distant cosmos, hints at an even grander, more profound choreography. The alignment of galactic spins with the colossal structures of the cosmic web. Imagine the universe not as a random scattering of galaxies, but as a vast, intricate network of filaments, walls, and voids, the cosmic web. This immense scaffolding, formed from the gravitational collapse of primordial matter, dictates where galaxies cluster and how they move. Intriguingly, astronomers have begun to uncover patterns suggesting that the axes of rotation of galaxies are not randomly oriented within this web, but often align with the directions of the cosmic filaments, or perpendicular to the walls of matter. This suggests that the initial subtle angular momentum present in the very early universe, long before galaxies fully formed, was not only conserved but also imprinted upon these large-scale structures, influencing the rotational direction of galaxies that would later coalesce within them. It implies a fundamental ancient connection between the universal expansion and the rotational dynamics of its largest components. A cosmic blueprint for spin laid down almost 14 billion years ago. Such alignments offer a tantalizing glimpse into the universe's primordial state, suggesting that the very large-scale distribution of matter dictated the initial rotational preferences that persist to this day. This is a testament to the elegant persistence of physical laws, stretching their influence across unimaginable distances and timescales. This grand alignment, however, is not without its intricate nuances. The nature of these spin alignments can vary depending on the mass of the galaxies and their position within the cosmic web. Smaller, less massive galaxies might show different alignment tendencies compared to their more massive counterparts, which are often found at the nodes where cosmic filaments intersect. These variations underscore the complexity of gravitational evolution, where local interactions and mergers can subtly reorient a galaxy's spin axis, even as the large-scale cosmic flow exerts its pervasive influence. Scientists continue to explore these patterns, using advanced simulations and deep field observations to unravel the precise mechanisms through which the initial cosmic turbulence translated into the organized yet varied spins of billions upon billions of galaxies. It is a slow, patient process of discovery, much like watching a complex dance unfold over an eternity, gradually revealing the hidden rules of its performance. This ongoing research illuminates how the universe's large-scale structure is not just a passive result of gravity, but an active participant in shaping the rotational destinies of its stellar islands. The concept of spin also extends into the realm of gravitational waves, those exquisite ripples in space-time that we have recently begun to detect directly. When two massive compact objects, such as black holes or neutron stars, orbit each other in a tightly bound binary system, they emit gravitational waves. These waves carry away energy and, crucially, angular momentum from the orbiting pair. As the system slowly loses angular momentum, the two objects spiral ever closer to each other, accelerating their orbital speed until they eventually merge in a cataclysmic event, releasing a final powerful burst of gravitational radiation. The spin of the individual objects, as well as their orbital angular momentum, is transferred into these space-time ripples, a subtle yet profound mechanism for the universe to shed excess rotational energy. The detection of these gravitational waves, notably by the LIGO and Virgo observatories, has not only confirmed a key prediction of Einstein's general theory of relativity, but has also provided direct evidence of how angular momentum is dissipated in the most extreme cosmic environments, offering a new window into the dynamic nature of space-time itself. It is a quiet reminder that even the most fundamental properties of the universe are not static, but are constantly, gently, being reshaped and rebalanced through these invisible cosmic undulations. Furthermore, the very act of observing rotation, of measuring spin, is deeply intertwined with our understanding of relative motion. Is there an absolute sense of rotation in the universe? According to the principles of modern physics, particularly general relativity, there is no preferred rest frame against which all motion, including rotation, can be absolutely measured. All motion is relative. However, the feeling of being spun, the experience of centrifugal force, is undeniably real. This apparent paradox was a profound source of contemplation for physicists like Ernst Mach and Albert Einstein. Mach's principle, a concept that influenced Einstein, suggests that inertia, the resistance of an object to changes in its state of motion, arises from the gravitational interaction with all other matter in the universe. In this view, the sensation of being spun is not due to absolute rotation, but rather to our rotation relative to the distant stars and galaxies, the vast cosmic background. While Mach's principle remains a philosophical idea rather than a fully formalized theory, it offers a deeply contemplative perspective on how our local experience of spin is intimately connected to the entire universe. It suggests that even our most immediate perceptions are echoes of the grand interconnected cosmic dance. Thus, the pervasive spin of everything in the universe is a multifaceted phenomenon, a grand narrative woven from the conservation of angular momentum, the subtle shaping power of tidal forces, the intricate quantum properties of particles, the generation of protective magnetic fields, the large-scale architecture of the cosmos, and even the very fabric of space-time itself. It is a testament to the elegant, enduring laws that govern our existence, creating a universe that is perpetually in motion, always transforming, yet always maintaining a profound, underlying balance. This ceaseless turning, from the smallest electron to the grandest galaxy, is a quiet symphony of physics, a constant reassuring hum in the vast silence of space. It is a reminder that even as we rest, the universe spins on, a magnificent and tranquil dance. This pervasive spin, as we have explored, is a multifaceted phenomenon, yet there remain further layers to its cosmic influence, revealing how even the invisible dictates the visible dance of rotation. One of the most compelling pieces of evidence for the ubiquitous nature of spin, and indeed for the existence of unseen matter, comes from observing the rotation curves of galaxies. When astronomers measure the speed at which stars orbit the center of a spiral galaxy, they find something truly unexpected. According to the visible matter, the stars, gas, and dust that emit light, the rotational speeds of stars should decrease significantly as their distance from the galactic center increases, much like planets orbiting the Sun. However, observations consistently show that stars in the outer regions of galaxies orbit at nearly the same speed as stars closer to the center, or even faster. This gravitational anomaly indicates that there must be far more mass present than what we can observe with our telescopes. This invisible, non-luminous substance is what we have come to call dark matter. It forms a vast spherical halo enveloping galaxies, its gravitational pull providing the additional mass necessary to explain these anomalous rotation curves. Without the immense unseen gravitational scaffold of dark matter, spiral galaxies would simply tear themselves apart due to their rapid spin. Thus, the very coherence and rotational stability of galaxies are intimately tied to this mysterious invisible component, a silent, unseen hand guiding the grand, swirling dance of billions of stars. It is a profound realization that the most majestic spins in the universe are not solely a product of visible matter, but are deeply influenced by forces beyond our direct perception. Expanding upon our earlier glimpse into the subtle distortion of space-time by rotating masses, let us consider the phenomenon of frame dragging, or the lens-thirring effect, in more detail. While most dramatically evident around rapidly spinning black holes, this effect is a universal prediction of Einstein's general theory of relativity. Any rotating mass drags the fabric of space-time around it. Even around our relatively sedate Earth, this effect is present, though incredibly subtle. Imagine space not as empty void, but as a dense, invisible syrup. As Earth spins, it very slightly stirs this syrup, causing a minuscule swirling current in space-time itself. This effect was famously measured by the Gravity Probe B mission, a satellite experiment launched by NASA in 2004. By precisely tracking the orientation of ultra-sensitive gyroscopes in orbit around Earth, scientists were able to detect the tiny, predicted frame-dragging effect, confirming that our planet's rotation indeed twists the very space-time in its vicinity. This means that a satellite orbiting Earth is not just moving through space, but is also gently carried along by the rotation of space-time itself, a silent, imperceptible current created by our world's spin. This subtle, almost poetic phenomenon reminds us that the universe is far more dynamic and interconnected than our everyday intuition suggests, where even the act of rotation can subtly ripple through the cosmic stage. Furthermore, the very limits of rotation play a critical role in shaping celestial bodies, preventing them from spinning themselves apart. Every object has a critical rotational speed at which the centrifugal force at its equator precisely balances the gravitational pull holding it together. If an object spins faster than this critical rate, it will begin to shed material from its equator. For stars, this can lead to dramatic effects, causing them to become highly oblate and possibly eject material into a circumstellar disk, enriching the surrounding space. For planets, extreme spin can result in rotational breakup, where the planet essentially flattens so much that it can no longer hold itself together as a single, coherent body. This principle sets a natural speed limit for the rotation of all celestial objects, dictating their maximum possible angular velocity and influencing their stable shapes. It is a powerful reminder that even in the absence of external forces, the internal dynamics of spin can dramatically shape the destiny of cosmic structures. A subtle yet profound self-regulation at play across the universe, preventing runaway rotation and preserving the integrity of worlds and stars. This interplay of rotation and centrifugal force is also beautifully demonstrated in the formation and stability of planetary rings, such as those famously encircling Saturn. These magnificent ring systems are not solid structures, but rather vast collections of countless ice and rock particles, ranging in size from microscopic dust grains to house-sized boulders, all orbiting the planet in a flattened disk. The prevailing theory suggests that these rings may have formed from the tidal disruption of a moon or a cometary body that ventured too close to the planet, crossing what is known as the Roche limit. Within this gravitational boundary, the planet's tidal forces become stronger than the moon's internal cohesive forces, tearing the smaller body apart into myriad fragments. These fragments, inheriting the angular momentum of the original body, then spread out into a thin, rotating disk around the planet. The centrifugal force from their orbital motion prevents them from falling back onto the planet, while gravitational interactions between the ring particles themselves and with shepherd moons help to maintain the ring's intricate structures and narrow divisions. It is a spectacular visible manifestation of rotation's power, transforming a shattered world into an ethereal, spinning halo, a cosmic masterpiece sculpted by the delicate balance of gravitational and rotational forces. And so, as we consider these deeper facets of spin, from the invisible embrace of dark matter guiding galactic twirls, to Earth's subtle dragging of space-time, to the critical limits that define an object's very existence, and the stunning artistry of planetary rings. We are left with an expanded sense of the universe's intricate design. Rotation is not merely a common observation. It is a fundamental language of the cosmos, speaking of origins, of stability, of transformation, and of the hidden forces that shape our reality. It is a profound yet calming thought to realize that this ceaseless motion, this eternal spin, is an essential part of the grand cosmic narrative, a gentle, persistent hum that resonates throughout every particle and every galaxy, inviting us into a deeper sense of wonder and connection. Beyond the gravitational mechanics that dictate the spin of large celestial bodies, the concept of rotation delves into even more abstract and fundamental aspects of reality, touching upon the very handedness or chirality of the universe. Chirality, derived from the Greek word for hand, describes objects that are non-superimposable on their mirror images, much like our left and right hands. In the realm of fundamental particles, this handedness is deeply tied to their intrinsic spin. For instance, neutrinos, those elusive, almost massless particles that stream through us by the trillions every second, are always observed to be left-handed, meaning their spin is oriented opposite to their direction of motion. Their antimatter counterparts, antineutrinos, are right-handed. This inherent asymmetry, a preference for one-handedness over another, is a profound feature of the weak nuclear force, one of the four fundamental forces of nature. The weak force, responsible for certain types of radioactive decay, famously violates parity symmetry, a principle that states the laws of physics should be the same even if we swap left and right. This cosmic handedness, rooted in the spin of elementary particles, hints at a deeper, subtle bias in the universe's foundational rules, a preference for a particular kind of twist or turn woven into the very fabric of existence. It suggests that spin is not merely a geometric property, but a descriptor of fundamental identity, differentiating particles in ways that profoundly influence their interactions. This concept of handedness, originating at the quantum level, also manifests itself on larger scales, albeit through different mechanisms. Consider the spiral patterns observed in many galaxies. While the direction of a galaxy's spiral arms, clockwise or counterclockwise, is not directly linked to fundamental particle handedness, the prevalence of one direction over another in certain cosmic structures could potentially reveal subtle, underlying influences. Some theories even speculate about the possibility of cosmic chirality on grand scales, where the universe itself might exhibit a preferred twist or handedness in its spatial distribution of galaxies, or even in the polarization of light from distant sources. While such large-scale cosmic handedness remains highly speculative and unconfirmed by current observations, the very contemplation of it invites us to consider spin as an inherent characteristic, a subtle bias in the cosmic architecture that might echo from the smallest quantum fluctuation to the broadest galactic sweep. It is a quiet, profound thought that the universe might possess a fundamental asymmetry, a preference for one direction of rotation over another, a subtle tilt in its grand design. The journey of spin from its primordial origins to its current manifestations also leads us to ponder its ultimate destiny. As the universe continues its relentless expansion, driven by the enigmatic dark energy, what becomes of all this rotational motion? While angular momentum is conserved in isolated systems, the universe as a whole is not truly isolated, and its components interact over eons. Gravitational interactions, as we have seen, can redistribute angular momentum, sometimes leading to mergers and the formation of larger, often more slowly rotating structures. Over truly immense timescales far beyond the lifespan of stars and galaxies, the universe faces several potential ultimate fates, each with implications for spin. In a scenario known as the heat death, the universe would expand indefinitely, becoming increasingly dilute and cold. Stars would burn out, black holes would eventually evaporate through Hawking radiation, and matter would decay into fundamental particles. In such an ultimate state of maximum entropy, where no energy gradients exist to drive further processes, the concept of coherent rotation would effectively cease. The once vibrant, spinning galaxies would be diffused, their constituent particles drifting apart into an almost infinite, silent void, their collective angular momentum spread so thinly as to be imperceptible, a final, tranquil dissipation of all cosmic motion. However, other theoretical scenarios propose different endings. In a Big Crunch scenario, if the expansion were to eventually halt and reverse, the universe would begin to contract, collapsing back upon itself into an incredibly hot, dense state, perhaps even a singularity. In such a contracting universe, the angular momentum of galaxies and other structures would become increasingly concentrated, potentially leading to extremely rapid rotations and violent interactions before the ultimate collapse. Yet another possibility is the Big Rip, where the acceleration of the universe's expansion grows so strong that it eventually tears apart all gravitationally bound structures, from galaxies to atoms, and even the fabric of space-time itself. In this extreme scenario, any coherent spin would be utterly obliterated, as the very bonds of matter and space are ripped asunder, leaving behind a formless, meaningless expansion. While these are theoretical horizons, far in the distant future, they remind us that the story of spin is an integral part of the universe's grand narrative, a tale of creation, evolution, and eventual transformation, all dictated by the immutable laws of physics. And as we conclude our deep dive into the fascinating world of cosmic spin, from the fundamental handedness of particles to the grand alignment of galaxies and the potential ultimate fates of rotation in the universe, we are left with a profound sense of its enduring presence. Spin is not just an incidental detail, it is a fundamental characteristic of reality, a silent, ceaseless dance that shapes the very existence of everything around us. It connects the quantum foam of the early universe to the majestic spirals of distant galaxies, revealing a universe that is always in motion, always evolving, yet always governed by elegant, underlying principles. Realize that this grand rotational symphony is an essential part of the cosmic tapestry. Let us now turn our attention to the fascinating implications of spin for the very structure of the early universe. Specifically, how the small primordial rotational components we discussed earlier might have influenced the formation of the first stars and galaxies. Theoretical models of cosmology suggest that the early universe was remarkably smooth, but not perfectly so. Tiny quantum fluctuations, amplified by cosmic inflation, created slight variations in density. Within these slightly denser regions, matter began to coalesce under gravity. As these regions contracted, any initial, albeit minute, rotational motion they possessed would have been conserved and amplified, leading to the formation of proto-galactic gas clouds already endowed with a net spin. This spin was crucial not just for the eventual flattening of galaxies into disks, but also for the very process of cooling and collapse that enabled star formation. Without sufficient angular momentum, a gas cloud would collapse too quickly, preventing the formation of stable, long-lived stars. The centrifugal force generated by rotation provides a crucial outward push, allowing the cloud to slow its collapse, radiate away energy, and fragment into smaller, denser clumps that can then form individual stars. This delicate balance, this cosmic dance between gravity pulling inward and rotation pushing outward, was essential for the universe to evolve from a homogeneous soup into the complex star-filled cosmos we inhabit. It underscores how the presence of spin, even in its most nascent forms, was a prerequisite for the emergence of the celestial architecture we now observe. Moreover, the phenomenon of spin plays a subtle yet critical role in the ongoing evolution and activity of active galactic nuclei, or AGNs. At the heart of most large galaxies, including our own Milky Way, resides a supermassive black hole. In active galaxies, this black hole is voraciously accreting matter from its surroundings, forming a brilliant accretion disk. As material spirals inward towards the black hole, its angular momentum must be shed, a process that generates immense heat and radiation, making these objects incredibly luminous. The spin of the central supermassive black hole itself is a crucial parameter, influencing the geometry and efficiency of this accretion process. A rapidly spinning black hole can sustain a more efficient accretion disk and generate more powerful jets, as the frame-dragging effect becomes more pronounced, twisting space-time to such an extent that it helps collimate and launch these outflows. These jets, extending far beyond the galaxy, can profoundly influence the intergalactic medium, heating gas and suppressing star formation in surrounding satellite galaxies. The rotational energy of these cosmic behemoths, therefore, is not merely contained within them. It actively sculpts and energizes their galactic environments, demonstrating the far-reaching impact of spin on cosmic evolution. It is a testament to the fact that rotation is an active, dynamic participant in the universe's grand narrative, a silent force shaping the destiny of entire galactic systems. The universality of spin also prompts us to consider the very nature of symmetry in physics. The conservation of angular momentum is a direct consequence of rotational symmetry, a fundamental principle stating that the laws of physics remain unchanged regardless of how we orient our coordinate system in space. In other words, the laws of nature do not depend on which way we are facing. This deep connection between symmetry and conservation laws, first articulated by the brilliant mathematician Emmy Noether, is one of the most profound insights in theoretical physics. Noether's theorem states that for every continuous symmetry in a physical system, there is a corresponding conserved quantity. Rotational symmetry gives rise to the conservation of angular momentum, just as translational symmetry, the idea that physics laws are the same regardless of where we are in space, leads to the conservation of linear momentum, and time translation symmetry, that physics laws are constant over time, leads to the conservation of energy. This elegant mathematical framework reveals that spin is not an arbitrary feature of the universe, but an inherent, necessary outcome of its fundamental symmetries. It suggests that the rhythmic turning of everything, from the quantum to the cosmic, is deeply embedded within the universe's most foundational architectural principles, a silent, unchanging truth that underpins all motion and interaction. And as we allow these intricate connections to settle within our minds, from the early universe's subtle swirls to the grand influence of spinning black holes and the fundamental symmetries that govern all motion, we find ourselves drawn into a deeper appreciation for the universe's elegant design. The pervasive spin is a constant reminder of the dynamic, interconnected nature of reality. We are part of a cosmos that is not only vast and mysterious, but also deeply ordered, where every rotation, every orbit, is a manifestation of enduring principles. May these thoughts about the ceaseless, purposeful dance of the universe carry you into a world of tranquil sleep, reinforcing the quiet wonder of your own place within this magnificent, spinning existence. Our contemplation of spin at various scales naturally leads to perhaps the most profound question. Could the entire universe itself be rotating? This is not a question easily answered, for it delves into the very large-scale structure and fundamental properties of space-time. The standard cosmological model, upon which much of our understanding of the universe's evolution is built, assumes that the universe is isotropic, meaning it looks the same in all directions, and homogeneous, meaning it has the same properties everywhere. A significant global rotation would fundamentally violate this assumption of isotropy, implying a preferred axis of rotation for the entire cosmos. Imagine a cosmic gyroscope, a single immense object slowly turning. Such a phenomenon would leave an unmistakable imprint on the universe, particularly on the cosmic microwave background, the faint afterglow radiation from the Big Bang, which serves as our earliest and most detailed map of the universe's primordial state. Scientists have meticulously searched for evidence of such global rotation by analyzing the cosmic microwave background data, especially from missions like the Planck satellite. This relic radiation emitted approximately 380,000 years after the Big Bang, is incredibly uniform across the sky, with only tiny temperature fluctuations. If the universe were indeed rotating, these minute fluctuations, often called anisotropies, would exhibit a distinct pattern, a subtle global twist or preferred direction. However, repeated analyses of the cosmic microwave background data have consistently revealed a remarkable degree of isotropy and homogeneity, placing extremely tight constraints on any possible global rotation. The consensus among cosmologists is that if the universe does possess a net spin, it is extraordinarily small, far too minuscule to be detected with current technology or to significantly impact the large-scale structure of the cosmos. This absence of detectable global rotation is a powerful affirmation of the cosmological principle, suggesting a universe that, on the grandest scales, is beautifully simple and symmetrical in its motion, a profound stillness underlying all the local dynamism. This quiet, large-scale non-rotation has deep implications for our understanding of the universe's geometry and its ultimate fate. If the universe were rotating, it might, for instance, influence the trajectory of light, causing it to bend differently depending on its direction of travel, or it could even affect the expansion rate of space itself. The fact that we observe such a uniform and isotropic cosmic microwave background supports models where the universe is spatially flat, or very close to it, and expanding uniformly in all directions without a preferred axis. This cosmic stillness, this lack of a universal spin, reinforces the idea of a universe that is not a closed system orbiting some external point, but rather an unfolding entity, expanding from within, without an outside, to turn relative to. It is a subtle, yet profound distinction that shapes our most fundamental theories about the cosmos, guiding our understanding of its origins and its future. The universe, in this sense, is not spinning like a top within a larger space. It is the space itself, gently stretching, without a rotational preference. Furthermore, the very concept of an absolute frame of reference for rotation has been a subject of deep philosophical and scientific debate for centuries. Isaac Newton, for example, believed in absolute space and time, implying that absolute rotation could be detected. However, thinkers like Ernst Mach later argued that the inertia of an object, its resistance to acceleration, including rotational acceleration, is not absolute, but arises from its. This Mach's principle, while not a fully formulated theory, profoundly influenced Albert Einstein's development of general relativity, which describes gravity not as a force, but as the curvature of space-time. In general relativity, the idea of absolute rotation becomes problematic. Rather, we speak of rotation relative to inertial frames, which are themselves influenced by the distribution of mass and energy in the cosmos. The frame dragging effect we discussed earlier, where massive rotating objects twist spacetime, is a direct manifestation of this relativistic view, demonstrating how local rotation can indeed influence its immediate surroundings. But on the largest scales, the observable universe appears to present a smooth, non-rotating background, suggesting that the sum total of all matter and energy in its grand configuration averages out to a state of rotational equilibrium, a kind of cosmic balance that allows for the emergence of the complex, local spins we observe. This profound lack of global cosmic spin, confirmed by the exquisite precision of cosmic microwave background observations, invites us to find a quiet beauty in the universe's fundamental symmetries. It suggests a cosmos that, at its deepest level, is remarkably unbiased, without a preferred direction or a favored axis of rotation. This underlying impartiality allows for the rich diversity of rotational phenomena we have explored, from the quantum spin of particles that build atoms to the majestic swirls of galaxies. Each local spin, each individual rotation, arises from specific conditions and interactions, but the universe as a whole maintains a serene, non-rotating equilibrium, a testament to the elegant principles that govern its vastness. Consider that while everything within the universe might be in a state of ceaseless, intricate spin, the universe itself, in its entirety, holds a magnificent, unchanging stillness, providing a steady backdrop for the dynamic ballet of. While the universe as a whole exhibits a remarkable lack of global rotation, the individual spins of its countless components are a constant symphony, a testament to the intricate dance of matter and energy. But how do we, from our tiny perch on a spinning planet, measure the rotation of distant stars and galaxies, objects light years away? The primary tool in this cosmic observatory is the Doppler effect. Just as the pitch of a siren changes as it moves towards or away from us, the light from a rotating star or galaxy exhibits a subtle shift in its wavelength. One side of the object, rotating towards us, will have its light slightly blue shifted, while the other side, rotating away, will be red shifted. By analyzing the spectral lines in the light, scientists can precisely measure these shifts, and in turn, determine the rotational velocity of the celestial body. This technique, known as Doppler broadening, provides invaluable insights into the internal dynamics of stars, the differential rotation of gas giants, and the complex velocity fields within galaxies. It is a remarkable feat of scientific ingenuity, allowing us to perceive motion across unimaginable distances, transforming the subtle whispers of light into concrete data about the universe's ceaseless pirouettes. Beyond this direct measurement, the study of asteroseismology, the science of stellar oscillations, offers another fascinating window into the internal rotation of stars. Just as seismologists study earthquakes to understand Earth's interior, asteroseismologists analyze the subtle pulsations and vibrations on the surfaces of stars. These stellar star quakes generate waves that propagate through the star's interior, and the patterns of these waves are profoundly influenced by the star's internal structure, density, and crucially, its rotational speed. By observing how these pulsations change over time, scientists can infer the rotation rates of different layers within a star, revealing complex internal dynamics that are otherwise hidden from direct view. For instance, studies have shown that the cores of some stars rotate significantly faster than their outer envelopes, a relic of their formation or a consequence of internal angular momentum transport. This intricate science allows us to peer into the very heart of spinning suns, understanding not just their surface turn, but the hidden layered ballet of their interiors, a profound insight into the mechanics of stellar evolution. The spin of stars also plays a crucial role in shaping their dramatic end-of-life transformations, particularly for those massive stars that explode as supernovae. A rapidly rotating massive star, upon reaching the end of its life, can undergo a core collapse that is significantly influenced by its initial angular momentum. While the core collapses to form a neutron star or black hole, the rapidly spinning material around it can create powerful, collimated jets of matter and energy that are launched outward during the supernova explosion. These jets, driven by the star's rotational energy and strong magnetic fields, can break through the star's outer layers, resulting in a highly asymmetric and energetic explosion. Some of the most powerful cosmic explosions, known as long-duration gamma-ray bursts, are thought to be the direct result of such a rotational collapse in a very massive, rapidly spinning star. This connection between stellar spin and the universe's most violent events highlights how fundamental rotation is, not just in the gentle birth of stars, but in their cataclysmic demise, enriching the cosmos with heavy elements that will eventually form new worlds and perhaps new life. Moreover, the spin of black holes, as we briefly touched upon, is not a static quantity, but can evolve significantly over cosmic time, often through the process of accretion. As a black hole continuously draws in matter from its surroundings, this infalling material carries its own angular momentum. Over immense periods, the black hole gradually spins up, increasing its rotational velocity. This increase in spin has profound consequences, as a more rapidly spinning black hole drags space-time more intensely, influencing the geometry of its accretion disk and the power of its jets. Interestingly, black holes can also undergo what are known as spin flips during mergers. When two spinning black holes collide and merge, the resulting single black hole can have its spin axis abruptly reoriented due to the complex gravitational interactions of the merging event. Such spin flips are a powerful signature that gravitational wave observatories like LIGO and Virgo are actively searching for, providing direct evidence of the dynamic nature of black hole spin and its profound influence on the very fabric of spacetime during these cataclysmic cosmic encounters. It reminds us that even the most enigmatic objects in the universe are not immutable, but are constantly evolving, their rotational properties reflecting the ongoing drama of the cosmos. And as we delve deeper into these intricate layers of spin, from the subtle shifts in starlight that reveal distant rotations to the internal pulsations of stars, the violent ends of massive suns, and the evolving dance of black holes, we find ourselves immersed in a universe of ceaseless, purposeful motion. This grand rotational tapestry, woven with the threads of angular momentum, gravity, and quantum mechanics, is not merely a collection of facts. It is a profound narrative of cosmic evolution. Realize that our own existence is part of this magnificent spinning story, dances with enduring grace and profound complexity, inviting us into deeper contemplation as we drift towards sleep. As we gently conclude our journey through the ceaseless turning of the cosmos, from the subatomic whirl of quantum spin to the majestic pirouettes of galaxies and the profound, measured stillness of the universe as a whole, we are left with a deeper appreciation for the elegant dance of existence. The pervasive spin is more than just a visible motion. It is a fundamental language of physics, a testament to the conservation of angular momentum, the intricate ballet of gravitational and tidal forces, and the subtle symmetries woven into the very fabric of reality. May these deep thoughts about why everything spins and how this universal motion shapes the worlds around us and our place within them. Remember that the universe is an astonishingly dynamic and beautifully ordered place, and you, in your quiet contemplation, are a conscious part of its grand, unending story. Fall asleep with this feeling of serene wonder and the boundless knowledge that connects us all to the ceaseless, graceful rhythm of the cosmos. Good night. Our journey into the profound implications of a cosmic cessation of spin begins by first understanding the universe as it is currently perceived. When we gaze into the vastness, observing the grand dance of galaxies, the slow waltz of star systems, and the intricate pirouettes of planets, we see rotation everywhere. Our own Earth spins on its axis, completing one rotation approximately every 24 hours, while also tracing its annual elliptical path around the Sun. The Sun itself, a colossal sphere of plasma, rotates once every 25 Earth days at its equator, simultaneously embarking on a 230 million-year orbit around the supermassive black hole at the center of the Milky Way. Our home galaxy, a majestic spiral, rotates with a differential speed, its outer arms lagging behind its core, a magnificent slow-motion swirl of hundreds of billions of stars. This ubiquitous motion, this swirling and turning, is a fundamental characteristic of celestial bodies, an enduring legacy of their formation within primordial spinning nebulae. Yet, when we consider the universe as a singular, encompassing entity, the concept of its spinning becomes far more nuanced. Modern cosmology, built upon decades of meticulous observation and theoretical refinement, strongly suggests that the universe, on its grandest scales, does not possess a net global rotation. This profound conclusion is primarily drawn from the remarkable isotropy of the cosmic microwave background radiation, often referred to as the afterglow of the Big Bang. This ancient light, bathing the entire cosmos, appears almost perfectly uniform in every direction we observe. If the universe had a significant overall spin, a deep intrinsic rotational momentum of space-time itself, we would expect to see subtle but discernible anisotropies in this background radiation. These would manifest as patterns of stretching or compression, a cosmic signature that would betray such a grand rotation. However, such patterns are conspicuously absent, leading scientists to infer that the universe as a whole is expanding uniformly, without a preferred axis of rotation. This absence of a global spin is a cornerstone of our standard cosmological model, known as the lambda-CDM model, which has been rigorously tested. It implies a universe that is largely homogeneous and isotropic, meaning it looks roughly the same in all directions and at all locations, once we average out local variations like galaxies and clusters. This foundational principle, often attributed to the groundbreaking work of scientists like Albert Einstein, whose general relativity describes gravity as space-time curvature, and Edwin Hubble, who observed the expanding universe, forms the essential backdrop against which we must consider our thought experiment. Now, let us turn our attention to one of the most bedrock principles in all of physics, the conservation of angular momentum. This is a law of profound elegance and universal applicability that governs all rotating systems, whether they are as small as an atom or as vast as a spiral galaxy. It states that the total angular momentum of an isolated system remains constant unless acted upon by an external torque. Imagine, if you will, an ice skater executing a graceful spin. As they pull their arms inward, bringing their mass closer to their axis of rotation, their rotational speed dramatically increases. This is a direct, observable manifestation of angular momentum conservation. The product of their moment of inertia, which describes how mass is distributed around the axis, and their angular velocity, their rotational speed, remains constant. Similarly, a vast, slowly rotating cloud of gas and dust far out in the emptiness of space will spin faster and flatten as it contracts under its own gravity. This process is fundamental to the formation of stars and planetary systems, transforming diffuse matter into compact, rotating celestial bodies. This is precisely why we observe such a wealth of rotational motion throughout the cosmos, from the smallest asteroids tracing their paths to the grandest spiral galaxies performing their stately dance. Each object carries an inherited angular momentum from the primordial material that coalesced to form it, a silent, enduring legacy of cosmic swirling that ensures stability and structure. So, if the universe as a whole is not thought to possess a net angular momentum in its expansion, what does it truly mean to imagine it stopping its spin? This hypothetical scenario invites us to consider not merely the cessation of rotation for observable matter, but rather a profound, instantaneous halt to any potential, subtle, or intrinsic rotational property of space-time itself, or a sudden collective cessation of the angular momentum of all its constituent parts, from the quantum foam to the supercluster. Such an event would not be a mere slowing down, but an absolute universal cessation of all angular motion, a complete cosmic stillness. It would imply a profound disruption, challenging our understanding of fundamental conservation laws and the very fabric of reality. The first, most immediate consequence of such a universal halt would be a catastrophic reordering of every celestial body. Planets currently held in a delicate gravitational balance by their orbital velocity would instantly lose the centrifugal force generated by their motion. This force, which effectively counteracts the inward pull of gravity, would vanish. Without it, planets would no longer be held in stable orbits. Instead, they would begin an inexorable plunge inward, drawn by the overwhelming gravitational pull of their central stars. Our own Earth, for instance, would no longer be held in its delicate balance around the Sun. The familiar path it traces would vanish, and it would initiate a direct accelerating fall towards our star, its surface rapidly heating under the increasing solar radiation, its atmosphere stripping away, transforming our vibrant world into a lifeless molten sphere long before impact. The Moon, too, would cease its orbit around Earth, beginning its own descent, perhaps colliding with our planet or being flung into the Sun as a stray projectile, highlighting the fragility of orbital mechanics. Similarly, stars within galaxies would lose their orbital velocity. The hundreds of billions of stars in the Milky Way, currently held in a gravitational equilibrium that allows for their sweeping spiral arms and stable stellar populations, would cease their coordinated movement. The immense gravitational forces at the galactic core, dominated by the supermassive black hole known as Sagittarius A star, would begin to pull all matter inward with unprecedented ferocity. Galaxies would no longer be flattened, rotating disks, but would collapse into denser, more spherical configurations, accelerating relentlessly towards their centers. The intricate structures we observe, the beautiful spirals and elliptical forms, are all products of angular momentum and the dynamic balance it creates. Without it, the very architecture of galactic clusters and superclusters would unravel, replaced by a chaotic inward rush, a cosmic implosion on a scale that defies easy visualization as the universe struggles to maintain structure without its rotational foundations. This thought experiment, while purely hypothetical and far removed from any plausible physical scenario, forces us to confront the profound elegance and absolute necessity of these conservation laws. The universe, in its current state, is a dynamic tapestry woven with threads of energy, linear momentum, and angular momentum. Each thread contributes to the stability, evolution, and very existence of cosmic structures. The conservation of angular momentum is not merely an abstract mathematical concept. It is the silent, pervasive force that dictates the formation of everything from spinning electrons, which possess an intrinsic angular momentum called spin, to the majestic rotation of galaxies. To imagine its cessation, even on a global scale, is to imagine a universe fundamentally unmade, stripped of the very processes that allow for the complexity, order, and dynamism we observe. It is a stark reminder of how deeply interconnected the laws of physics are, and how a change in one fundamental principle could ripple through all scales of existence, reshaping reality in ways almost beyond our comprehension. This cosmic stillness, this sudden absence of the spin that defines so much of our observed cosmos, would be a testament to the quiet yet absolute power of these immutable laws. It underscores that our very existence, the stability of our planet, and the structure of galaxies are all sustained by these invisible, tireless principles, quietly orchestrating the grand symphony of the cosmos. Having explored the macroscopic unraveling of celestial structures, our thought experiment now guides us to consider the deeper, more profound implications for the very bedrock principles of physics. A universal cessation of spin would not merely halt the majestic dance of galaxies and the intricate orbits of planets. It would challenge the fundamental conservation laws that underpin our understanding of reality, most notably the conservation of energy and the intimate relationship between symmetries and these laws, as articulated by the brilliant mathematician Emmy Noether. Noether's theorem, a cornerstone of modern physics, elegantly demonstrates that for every continuous symmetry in nature, there exists a corresponding conservation law. The conservation of angular momentum, which we discussed, is a direct consequence of the universe's rotational symmetry. The idea that the laws of physics remain unchanged regardless of how we orient our coordinate system in space. If the universe were to suddenly cease all rotation, it implies, in a profound sense, that this fundamental rotational symmetry has been broken, or perhaps even momentarily redefined, leading to a cascade of effects that would shake the very foundations of physical law. The most immediate and perhaps most unsettling implication beyond the direct gravitational collapses would be for the conservation of energy. All rotating bodies, from the smallest subatomic particles to the largest superclusters, possess rotational kinetic energy. If this universal spin were to abruptly cease, this immense quantity of energy would not simply vanish. Energy, as we understand it, cannot be created or destroyed, only transformed. The sudden disappearance of all rotational kinetic energy would represent an explicit violation of this most fundamental of conservation laws. Where would this energy go? Would it be instantaneously converted into a burst of thermal energy, causing the universe to flare with unimaginable heat? Or perhaps into a cascade of gravitational waves rippling through the newly static space-time? The very act of this hypothetical stopping forces us to confront the limits of our known physics, suggesting that such an event, if it were even conceivable, would necessitate an entirely new understanding of energy transformation, or indeed a universe where one of its most cherished principles is no longer valid. This is not a dramatic prediction, but rather a calm, intellectual puzzle, highlighting the deep interconnections within our physical theories. Furthermore, this universal halt to rotation would inevitably touch upon the very nature of space-time itself and its relationship to motion and inertial frames, concepts deeply rooted in Albert Einstein's theories of relativity. While the universe, on its largest scales, is not thought to have a net global rotation, the hypothetical stopping of its spin implies the establishment of a universally preferred frame of rotational rest. This is a subtle but crucial distinction. In general relativity, massive rotating objects, such as black holes or even spinning planets, exert a phenomenon known as frame dragging, where they literally twist and drag space-time around them. If all rotation were to cease, this intricate dance of space-time around massive objects would also halt. The very texture of space-time would become uniformly static in its rotational aspect. This would not necessarily violate special relativity's principle of no absolute linear motion, but it introduces a universal no-spin reference frame, a concept that, while not directly contradictory to the spirit of relativity, would certainly alter our relativistic understanding of a cosmos where all motion is inherently relative. The profound quietude of a non-rotating universe would thus extend to the very geometry of existence, simplifying some aspects of space-time while simultaneously creating new philosophical and physical dilemmas. Descending to the microscopic realm, the implications become even more profound. Consider the intrinsic angular momentum of particles, known as quantum spin. This is not a classical rotation in the sense of a tiny ball spinning on its axis, but a fundamental quantum property of elementary particles like electrons, protons, and neutrons. It is spin that dictates how particles interact, how they arrange themselves in atoms, and ultimately, how matter itself forms stable structures. If the universe were to stop spinning in a way that affected even these intrinsic quantum properties, the very fabric of matter would unravel. Electrons, losing their characteristic spin, might no longer behave as fermions, particles that obey the Pauli exclusion principle, which prevents two identical electrons from occupying the same quantum state. Without this principle, atoms would collapse, as electrons would no longer be forced into distinct energy levels and orbitals. The stability of atoms, the very possibility of chemistry, and therefore the existence of molecules, stars, planets, and life itself, would be utterly extinguished. This would be a redefinition of reality at its most fundamental level, transforming the familiar universe into something utterly alien and formless, a silent testament to the vital invisible role of quantum spin in sustaining existence. It's a thought that quietly humbles us, reminding us that the deepest principles of the cosmos are often found in the most minute, unseen details. Such a universal cessation of spin, therefore, cannot be easily dismissed as a mere thought experiment. It becomes a profound probe into the interconnectedness of physical laws. For angular momentum to cease, an external torque would be required. But for the entire universe to stop spinning, what external force could possibly act upon it? This question highlights the extraordinary nature of the universe as a truly isolated system, where such external influences are, by definition, non-existent. The very idea of an external torque acting on the cosmos contradicts the basic premise of a self-contained universe. This leads us to ponder the limits of our physical models and the boundaries of what is conceivable within the framework of known physics. The laws of conservation, in their quiet constancy, are not arbitrary rules. They are reflections of deep symmetries woven into the very structure of space-time. To imagine them broken is to imagine a universe fundamentally different from our own, a universe where the familiar patterns of cause and effect, of order and transformation, no longer hold sway. It is a thought that invites a deep, calm contemplation of the elegant scaffolding that supports everything we perceive. The cascade of effects from a universe stripped of its spin would extend far beyond the mere gravitational collapse of celestial bodies and the unraveling of atomic structures. If we consider the very foundations of physical law, particularly the conservation of linear momentum, we encounter another profound disruption. Just as rotational symmetry underpins the conservation of angular momentum, the translational symmetry of space, the idea that the laws of physics are the same no matter where you are in the universe, is inextricably linked to the conservation of linear momentum. Linear momentum, the product of an object's mass and its velocity, is conserved in an isolated system. This means that if an object is moving, it will continue to move at the same speed and in the same direction unless an external force acts upon it. If the universe were to cease all motion, not just rotational, but also linear, then every particle, every galaxy, every wave would instantaneously lose its momentum. This would mean that the very concept of motion, as we understand it, would be fundamentally altered or even abolished. Imagine a single photon, a particle of light, traversing the cosmos. Its journey, its very existence as a moving entity, embodies linear momentum. If the universe were to suddenly impose a universal stillness, stopping all linear motion, that photon would cease to propagate. Light itself would freeze, becoming an eternal static pattern. Such a universal stillness would represent a breaking of translational symmetry, an instantaneous halt to all movement across the cosmic expanse. What force, what mechanism could possibly enact such a uniform deceleration across a universe so vast, affecting every single speck of matter and energy simultaneously? This thought highlights the interconnectedness of our fundamental laws. To break one symmetry is often to break others, revealing the delicate, intricate balance upon which our reality rests. The universe, as we know it, is a tapestry of motion, and to pluck out the threads of linear and angular momentum would be to unravel the entire design, leaving behind a stillness so absolute it borders on the inconceivable. This profound cessation of all motion would dramatically impact the very definition of time. Our experience of time, our ability to measure its passage, is inherently linked to change, to events unfolding, to the movement of celestial bodies, and to the ceaseless dance of particles. Consider the most fundamental clocks we possess, the oscillations of atoms, the decay of radioactive isotopes, or even the simple act of a pendulum swinging. Each of these relies on motion, on a process of change, to mark the passage of seconds, minutes, and eons. In a universe where all motion has ceased, where every particle is utterly still, would time itself lose its meaning? Without the ticking of atomic clocks, the orbiting of planets, or the subtle vibrations of atoms within their crystalline lattices, the markers by which we delineate past, present, and future would vanish. Time might become a frozen, static dimension, a mere coordinate without any dynamic flow, a concept explored in some philosophical interpretations of general relativity, where space-time is seen as an unchanging block. Such a universe would be a grand, silent tableau, a cosmic snapshot where the concept of before and after would become a relic of a dynamic past, if such a past could even be meaningfully said to exist. It forces us to confront the idea that time is not an external river flowing independently, but an emergent property of the universe's ceaseless activity. If that activity were to halt, time's flow might simply cease, leaving existence in an eternal, changeless now. This is a quiet, contemplative challenge to our most ingrained intuitions about reality, suggesting that the very rhythm of our lives, the progression of our thoughts, and the unfolding of our personal histories are deeply intertwined with the cosmic dance of motion and change. The implications for the fundamental forces of nature would also be staggering. While electromagnetic forces, responsible for holding atoms and molecules together, do not directly rely on the macroscopic spin of the universe. Their very operation depends on the existence of charged particles and their interactions. If, as speculated in the previous chapter, quantum spin were to be affected, the intrinsic angular momentum of elementary particles like electrons and quarks, the stability of electrons and protons, and thus the very existence of electric charge as a stable property, could be compromised. Without stable charges, the electromagnetic force would cease to function as we know it, leading to the disintegration of atoms and the dissolution of all chemical bonds. Imagine the very structure of your hand dissolving, not violently, but simply ceasing to be held together as the electrostatic repulsion and attraction between particles vanish. The strong nuclear force, the most powerful force in the universe, which binds quarks into protons and neutrons and holds atomic nuclei together, also relies on the quantum properties, including spin of these particles. A universe without quantum spin, or with its properties drastically altered, would be a universe where atomic nuclei could not form or would instantly fragment. Stars, the cosmic furnaces that forge elements, would be rendered inert, as the conditions necessary for nuclear fusion, which depends on the intricate interplay of these forces, would no longer exist. Similarly, the weak nuclear force responsible for radioactive decay and certain stellar fusion processes would also be profoundly impacted, likely rendering stars unable to burn and elements unable to transmute. In essence, the cessation of spin would not just dismantle structures, but would tear apart the very forces that build and sustain them, leading to a state of ultimate, formless chaos, where even the most basic components of matter cannot exist. The very concept of matter itself, as an organized collection of particles, would become meaningless. This unsettling scenario brings us back to Emmy Noether's theorem with renewed appreciation. Her work illustrates that the conservation laws are not arbitrary rules, but rather emerge from the deep inherent symmetries of space-time. The conservation of energy arises from the uniformity of time, constant across time. The conservation of linear momentum stems from the uniformity regardless of your position. And crucially, the conservation of angular momentum derives from the isotropy regardless of your orientation. If the universe were to stop spinning and stop moving, it would imply a breaking of these fundamental symmetries. Such a universe would be one where the laws of physics themselves are no longer globally consistent, where the rules could change depending on where you are or which way you are facing, or even when you are observing. This would be a universe fundamentally unpredictable, a state of cosmic disarray where the very framework for scientific inquiry, for prediction, for understanding, would dissolve. It's a reminder that the elegant scaffolding of mathematics and symmetry is not merely a description of reality, but perhaps its very essence. In this profoundly static cosmos, even the act of observation, the very process of becoming aware, would be challenged. Our senses, our thoughts, our consciousness all rely on dynamic electrochemical processes, on the movement of signals, on the flow of energy. Neurons fire, chemical neurotransmitters cross synapses, electrical impulses propagate through intricate networks, all of which are forms of motion and energy transfer. In a universe where all motion and change have ceased, where energy transformations are impossible, the very mechanisms that allow for thought and perception would likely be impossible. Our own existence, a fleeting pattern of energy and information, is dependent on the dynamic, ever-changing nature of the universe. To imagine a universe without spin, without motion, is to imagine a universe without the capacity for life, without the possibility of an observer to even ponder its stillness. It is a quiet reflection on our own place within the grand energetic dance of the cosmos, reminding us that we are not merely spectators, but integral participants, woven from the same dynamic threads that make up the stars and galaxies. Our ability to perceive, to question, to understand is itself a testament to the ongoing active nature of the universe. This contemplation, while stretching the boundaries of our imagination, ultimately reinforces the profound beauty and inherent stability of our actual universe. The fact that angular momentum is conserved, that energy is conserved, that linear momentum is conserved, these are not accidental features, nor are they mere conveniences for our equations. They are elegant reflections of a cosmos that is profoundly symmetrical, remarkably consistent, and therefore wonderfully understandable. The gentle, predictable flow of the river of reality, with its swirling eddies of galaxies and its steady currents of planetary orbits, is a testament to these unbreakable laws. It is this steadfast adherence to fundamental principles that allows for the intricate complexity of life to emerge, for stars to burn steadily for billions of years, and for consciousness to arise and ponder these very mysteries. The universe, in its perpetual ordered motion, offers a canvas for endless discovery and a tranquil backdrop for our own fleeting existence. And as we consider the silent, static alternative, a realm devoid of all motion and change, we can perhaps find an even deeper sense of peace in the dynamic, vibrant reality that surrounds us, knowing that its fundamental laws are steadfast and true, quietly ensuring the cosmic order and the very possibility of our being. Having delved into the profound implications for both the grand structures of galaxies and the very stability of matter at its quantum foundations, our thought experiment now turns its gaze upon the ultimate canvas of existence, space-time itself. If all spin, all motion, were to instantaneously cease across the entire universe, it would fundamentally reshape the dynamic fabric woven by mass and energy. Albert Einstein's general theory of relativity teaches us that space-time is not a passive, rigid stage, but an active participant, a flexible medium that is warped and curved by the presence of matter and energy. This curvature is what we perceive as gravity, guiding the paths of planets, stars, and even light. In a universe where all linear and angular motion has vanished, the dynamic aspects of this curvature would undergo an unimaginable transformation. Imagine space-time as a vast, flowing river. In our universe, this river is constantly in motion, with eddies around stars and galaxies, and sweeping currents guiding all celestial bodies. Now envision this cosmic river suddenly freezing solid. No more currents, no more eddies, just an unyielding, static structure. The intricate phenomenon of frame dragging, where massive rotating objects subtly twist space-time around them, would vanish entirely. Black holes, those cosmic behemoths, would still possess immense gravitational fields, but the dynamic, swirling nature of their space-time distortion, arising from their rotation, would cease. Their event horizons would become perfectly spherical, devoid of any rotational effects, like silent, unmoving cosmic sculptures. This absolute stillness would simplify the geometry of space-time in one sense, stripping away its dynamic twists and turns, yet it would render it profoundly alien, a universe of pure, frozen geometry where the narrative of evolution and change could no longer unfold. This brings us to a particularly intriguing philosophical and physical concept: the block universe. In this view, often considered a natural consequence of relativity, all moments in time, past, present, and future, are equally real and exist simultaneously, laid out like a four-dimensional landscape. Our experience of time passing is merely our consciousness moving through this pre-existing landscape. In a universe where all motion has stopped, where there are no events to mark the flow of time, this block universe perspective takes on an even more stark and literal meaning. If nothing ever changes, if no particle moves, no star burns, no thought forms, then the very concept of a present moment advancing into a future becomes meaningless. The universe would be eternally fixed, a single unchanging cosmic tableau. Such a scenario challenges our deepest intuitions about causality. We live in a universe defined by cause and effect. One event leads to another, creating a chain of consequences. But if all motion and change are absent, if time is frozen, then the very mechanism of causality would dissolve. An effect cannot follow a cause if there is no temporal progression, no dynamic interaction. Information, too, is deeply intertwined with these concepts. In physics, information is often considered a fundamental entity, never truly lost, only transformed or scrambled. If all physical processes cease, if atoms cannot interact, if light cannot propagate, then the transmission and processing of information, from the simplest particle interaction to the most complex biological thought, would become impossible. The universe would be a realm where information, though perhaps existing in some static, encoded form, could never be accessed, processed, or exchanged, a silent library where all pages are eternally bound shut. And what of the observer in such a profoundly static universe? Our consciousness, our very ability to perceive and ponder these cosmic mysteries, is a product of incredibly complex, dynamic electrochemical processes within our brains. Neurons fire, electrical signals propagate, chemical reactions unfold, transformation. Then the intricate dance of particles that constitutes a living, thinking being would also halt. The chemical gradients that drive cellular activity, the electrical impulses that form thoughts, the very metabolic processes that sustain life, all would become impossible. There could be no observers, no consciousness, no awareness to witness this ultimate stillness. The universe would exist, perhaps, in a state of absolute, unobserved repose, a cosmic artifact devoid of any internal experience or external interaction. To their furthest reaches serves as a powerful reminder of the delicate yet robust foundations upon which our reality is built. The conservation laws of energy, linear momentum, and angular momentum are not merely abstract mathematical constructs. They are the elegant expressions of fundamental symmetries in space-time that ensure a dynamic, evolving, and understandable cosmos. The fact that the universe does spin on local scales, that matter does move, that time does flow, and that consciousness does emerge to observe it all, is a testament to the profound and subtle interplay of these principles. Our actual universe, in its ceaseless, ordered motion, is not merely functional. It is a marvel of inherent stability and dynamic potential. It is a universe where the laws of physics are consistent, allowing for the emergence of complexity, the formation of stars and planets, and the eventual blossoming of life and thought. This vibrant, ever-changing reality, sustained by its unbreakable laws, offers a tranquil backdrop for our existence, a quiet reassurance that the cosmic dance continues, allowing us to find peace in its enduring rhythm. It is a universe that, far from being static, breathes and evolves, carrying us along in its magnificent, unending story. As we continue to navigate the abstract landscapes of our thought experiment, it becomes increasingly clear that the notion of a universe entirely ceasing its spin and motion is not merely physically improbable, but conceptually challenging. The very act of stopping implies a violation of fundamental principles we hold dear. If we consider the universe as a singular, isolated system, then for its total angular and linear momentum to vanish, an external agent, a cosmic hand, would be required to exert an instantaneous, universal torque and force. Yet, by definition, there is nothing outside the universe to exert such a force. This thought experiment, therefore, serves not as a prediction of what could happen, but as a profound tool for appreciating the intricate web of laws that do govern our reality. It highlights how deeply ingrained and self-consistent these principles are, revealing the universe as a system that inherently resists such absolute, abrupt cessation of its fundamental attributes. The stability we experience, the predictable dance of celestial mechanics, and the very existence of structured matter are all testaments to this intrinsic resistance to radical, uncaused change. This resistance brings us to the concept of inertia, a property of matter that describes its tendency to resist changes in its state of motion. In our actual universe, a body at rest tends to remain at rest, and a body in motion tends to remain in motion with acted upon by an external force. This is Newton's first law, a cornerstone of classical mechanics. But in a universe where all motion is suddenly halted, the very meaning of inertia becomes convoluted. If everything is instantaneously brought to a standstill, does inertia still exist as a property, or is it rendered moot? The stopping implies that the resistance to change in motion has been overcome for every single particle simultaneously. This would suggest an instantaneous and universal application of a force that counters every single inertial tendency, a cosmic braking system operating on an unprecedented scale. Such a mechanism would be fundamentally antithetical to the very concept of inertia, implying that matter itself has lost its inherent tendency to maintain its state of motion. It would be a universe where the fabric of existence no longer remembers its previous state of movement, a profound erasure of kinetic history. This quiet observation underscores the active role of inertia in maintaining the coherence and continuity of physical processes. Let us further consider the role of dark energy. As we know, our universe is not merely static. It is expanding, and this expansion is accelerating due to the mysterious influence of dark energy. If our hypothetical stopping of the universe's spin and motion were truly universal, it would logically entail a cessation of this expansion as well. For space itself to stop stretching, the repulsive force attributed to dark energy would have to be neutralized or overcome. This would signify a profound shift in the fundamental properties of the vacuum. Dark energy, currently understood as an intrinsic property of space, a kind of inherent pressure that pushes the cosmos apart, would either vanish or its effects would be overridden by an even more dominant universal force towards absolute stillness. This transformation would plunge the universe into a new, unprecedented state of static equilibrium, where the cosmic background radiation, the relic heat from the Big Bang, would no longer cool as space expands, but rather remain uniformly distributed, a frozen echo of a dynamic past. The very large-scale structure of the universe, the cosmic web of galaxies and voids, would cease its slow evolution, becoming an unchanging monument to a halted expansion. This imagined cessation of expansion, coupled with the absence of all other motion, would truly define a universe of ultimate, unyielding stasis, a silent, vast museum of what once was. This reflection gently guides us to appreciate the subtle, yet powerful, continuous unfolding of our universe, a testament to the persistent influence of forces we are only just beginning to comprehend. The implications for thermodynamics, the study of energy and heat, would be equally profound. The concept of entropy, often described as a measure of disorder or the dispersal of energy, plays a central role in the universe's evolution. In our dynamic cosmos, entropy is constantly increasing, driving processes from the burning of stars to the mixing of gases. This inexorable march towards greater disorder is what gives time its arrow, its direction from past to future. But if all motion, all change, all energy transformations were to suddenly stop, the universe would reach a state of ultimate, frozen equilibrium. Entropy would effectively cease to increase, locked into a maximum state of unchanging disorder. This would not be the heat death envisioned by some cosmologists, where the universe slowly cools to a uniform, low-energy state, but rather an instantaneous motion death, where the very mechanisms of energy exchange and transformation are abolished. The universe would become a perfect crystal of stillness, where nothing moves, nothing changes, and therefore no work can be done, no information can be processed, and no new structures can emerge. It would be a cosmos devoid of all thermodynamic activity, a profound and absolute cessation of the very engine that drives cosmic evolution. This silent, frozen state is a powerful contrast to the vibrant, messy, and wonderfully creative universe we inhabit, where the constant striving towards equilibrium paradoxically gives rise to boundless complexity and emergent phenomena, including ourselves. It allows us to appreciate the delicate balance between order and disorder that permits our existence, a balance that is only possible through continuous motion. To their furthest reaches, ultimately serves as a quiet reaffirmation of the profound beauty and inherent stability of the dynamic universe we actually inhabit. Theoretical constructs. They are the silent, steadfast guardians of cosmic order. They are the underlying symmetries that permit the grand ballet of galaxies, the steady burning of stars, the delicate formation of planetary systems, and the intricate dance of particles that gives rise to life itself. It is precisely because these laws hold true, because motion and change are inherent properties of our reality, that the universe is capable of such breathtaking complexity and enduring beauty. Without them, there would be no cosmic evolution, no stars to forge the elements, no planets to harbor life, and no consciousness to marvel at the universe's wonders. The vibrant tapestry of our existence, with its ever-unfolding narrative, depends utterly on this continuous ordered flux. This thought experiment, therefore, becomes a quiet celebration of the universe's inherent dynamism, a profound appreciation for its ongoing active nature. It reminds us that our very being, our ability to think, to feel, to perceive, is inextricably linked to the ceaseless ordered activity of the cosmos. Every breath we take, every beat of our heart, every thought that flickers through our mind is a testament to the continuous flow of energy and momentum, a micro-reflection of the grand cosmic dance. We are not separate from this dynamism. We are an integral part of it, a transient yet wonderfully complex pattern of energy and information, momentarily aware of our place in this vast, ever-spinning, ever-moving reality. The profound stillness of a universe without spin would be an absolute silence, a realm where even the whisper of a thought would be an impossibility, where existence would be reduced to a timeless, unchanging potential, never actualized. But the universe we know is full of the quiet hum of motion, the gentle whispers of gravitational waves, and the soft glow of distant stars, all orchestrated by these elegant, unbreakable laws. This sustained, intricate motion is what allows for the rich tapestry of existence, permitting phenomena from the simplest atomic interaction to the most complex biological system, including our own conscious minds. In contemplating its hypothetical absence, we gain an even deeper appreciation for the vibrant, living cosmos that cradles us. It is a tranquil reassurance that the fundamental principles, allowing the great story of existence to continue its magnificent, unending unfolding. This dynamic universe is not just a stage for life, but the very source of its potential, a continuous wellspring of change and emergence, and in our own place within it. Our journey through the speculative realm of a non-spinning, non-moving universe has revealed a cosmos profoundly different from the one we inhabit. It forces us to appreciate the delicate balance and intricate interdependencies that define our reality. As we contemplate this ultimate stillness, another layer of its profound implications comes into focus. The very nature of the fundamental constants that underpin all physical laws. These constants, such as the speed of light, the gravitational constant, Planck's constant, and the elementary charge, are the bedrock parameters that define the universe's behavior. They are assumed to be universal and unchanging, allowing for the consistent operation of physics across all of space and time. In a universe where all motion and interaction have ceased, the stability and meaning of these constants would face an unprecedented challenge. Consider the speed of light, a constant that sets the ultimate speed limit for information and energy transfer. If light itself were frozen, unable to propagate, then the very concept of a finite universal speed limit becomes moot. The constant would still exist as a numerical value, perhaps, but its operational significance, its role as a dynamic constraint on interactions, would vanish. Similarly, Planck's constant, which governs the quantum realm and the quantization of energy, is inextricably linked to dynamic processes, to the discrete jumps of energy levels, and the wave-particle duality of matter. In a universe of absolute stasis where particles no longer interact or move, the quantum dance that Planck's constant describes would cease. The very parameters that allow for the emergent complexity of our universe, from the stability of atoms to the formation of stars, are profoundly tied to motion and interaction. A universe without spin, without movement, would imply a cosmos where these constants, though perhaps numerically present, no longer possess their dynamic, generative power. It would be a universe of fixed values, but no active physics, a silent, unmoving equation without a solution. This profound stillness would also extend to the concept of cosmic evolution. Our universe, over its 13.8 billion-year history, has undergone a magnificent journey of transformation. From the primordial plasma of the Big Bang through epochs of nucleosynthesis, star formation, galaxy assembly, and the emergence of life, the cosmos has been a canvas of continuous dynamic change. This evolution is driven by the interplay of forces, the flow of energy, and the constant rearrangement of matter, all orchestrated by the conservation laws and fundamental constants. The very possibility of evolution, of change over time, would be extinguished. There would be no stellar nurseries birthing new suns, no supernovae enriching the cosmic medium with heavy elements, no planets forming from swirling disks of dust and gas. The universe would be a frozen tableau, an eternal snapshot of the instant motion ceased, forever locked in a state of suspended animation. This thought invites us to reflect on the deep connection between dynamism and potential. In our universe, motion is the engine of creativity. It is the restless movement of particles, the gravitational dance of galaxies, and the energetic processes within stars that generate the conditions for novelty, for complexity, for the emergence of structures that are greater than the sum of their parts. From the initial quantum fluctuations that seeded the large-scale structure of the cosmos to the intricate chemical reactions within a living cell, motion is the prerequisite for becoming. A universe without motion is a universe without potential, without the capacity to create, to transform, to evolve. It would be a realm of absolute actuality, where everything that can be is already manifest in an unchanging form, and nothing new can ever arise. This profound absence of cosmic becoming offers a quiet contrast to the vibrant, ever-renewing universe we inhabit, a universe that is a continuous testament to the power of dynamic processes. Furthermore, consider the profound implications for our scientific methodology. The very act of scientific inquiry, of observation, experimentation, and measurement relies on the dynamic interaction between an observer and the observed. We detect light from distant galaxies, measure the forces between particles, and track the motion of celestial bodies. All these acts involve the transfer of energy and information, processes that depend on motion. In a universe of absolute stillness, where light is frozen and particles are inert, there could be no observations, no experiments, no measurements. Scientific knowledge, as we understand it, would be impossible to acquire or verify. The universe would be an unreadable book, its pages forever blank, its stories untold. The very enterprise of seeking to understand the cosmos, the journey of discovery that defines humanity's intellectual quest, would be rendered meaningless. This thought highlights the active, participatory nature of our relationship with the universe. We are not passive observers of a static tableau. We are active participants in a dynamic, unfolding reality. Our minds, our instruments, our very capacity for curiosity are products of this ceaseless motion and change. To imagine a universe without these dynamic underpinnings is to imagine a universe where the light of inquiry, the spark of understanding, could never ignite. It is a quiet reminder that our ability to comprehend the universe is itself a gift of its inherent dynamism, a profound connection between the observer and the observed, woven into the very fabric of existence. The consistent, predictable nature of the conservation laws allows for the accumulation of knowledge, for the building of theories, and for the shared understanding that binds the scientific community. The universe in its continuous ordered flux, exploration of a hypothetical, non-spinning universe, devoid of all motion, serves ultimately as a profound thought experiment, illuminating the indispensable role of the conservation laws in shaping the dynamic, vibrant reality that we actually inhabit. It underscores that these principles, far from being mere constraints, are the very conditions that enable the universe to be a canvas for complexity, structure, and emergent phenomena, including life itself. The stability of the fundamental constants which we discussed, and the integrity of the conservation laws, arbitrary rules. Instead, they are the elegant scaffolding upon which cosmic creativity is built, permitting an ongoing symphony of transformation rather than an eternal, silent stasis. In our real universe, dynamism is woven into the very fabric of existence, even at scales far beyond our direct perception. Consider the quantum fields that permeate all of space, giving rise to elementary particles. Even in the deepest vacuum, far from the gravitational embrace of stars and galaxies, these fields are never truly at rest. They hum with latent energy, giving rise to fleeting pairs of virtual particles and antiparticles that flicker into existence and vanish almost instantaneously, a ceaseless, unobservable dance governed by the uncertainty principle. This inherent restlessness, this continuous bubbling of the quantum foam, is a direct consequence of the universe's fundamental laws. It is a subtle, yet powerful form of motion and energy fluctuation that constantly seeds potential, even in what appears to be empty space. This contrasts sharply with the static void we imagined, where even the quantum realm would be frozen into absolute stillness. This continuous, low-level activity within the vacuum, a concept developed by pioneering physicists like Paul Dirac and later explored by many others, demonstrates that the universe is fundamentally alive with potential, a wellspring of change that would be absent in a truly static state. This fundamental dynamism, governed by the very conservation laws we have carefully explored, is the wellspring of all complexity. It is the persistent, ordered movement of matter and energy that allows for the long, stable burning of stars, forging the heavy elements essential for planets and life. It is the conservation of angular momentum that enables vast clouds of gas and dust to coalesce into rotating disks, from which solar systems are born, rather than collapsing chaotically into formless blobs. The precise interplay of these constants and laws allows for the conditions necessary for complex chemistry, for the intricate self-assembly of molecules into cells, and for the long, stable evolution of biological systems capable of thought and awareness. Our own existence, a marvel of organized complexity, is a direct, vibrant expression of this dynamic, law-abiding cosmos. We are not merely observers, but integral parts of this grand, ongoing process, a brief yet conscious pattern within the universe's ceaseless flow. The universe, therefore, functions as a remarkably self-regulating system. The conservation laws ensure a kind of cosmic resilience, preventing the catastrophic unraveling we envisioned in our thought experiment. Energy doesn't just disappear, it transforms, driving new processes. Momentum isn't simply lost, it is transferred, maintaining the intricate balance of interactions. These laws provide a framework for stability and continuity, ensuring that while the universe undergoes immense transformations, stars dying, galaxies colliding, new structures forming, the fundamental principles governing these changes remain constant. This enduring consistency allows for cosmic evolution to proceed in a coherent, predictable manner, offering a deep sense of order amidst the grandeur of cosmic events. It is a profound, quiet reassurance that the universe is not capricious, but operates on principles that are both elegant and steadfast, allowing for the slow, majestic unfolding of its story. When we consider the fine-tuning of the universe, often pondered in philosophical circles, it is not merely about the specific values of constants, but also about the validity and interaction of these conservation laws. If these laws were slightly different, or if they did not hold universally, the dynamic, evolving universe we know would be impossible. The universe's parameters appear precisely calibrated to allow for the emergence of complexity, for the formation of stable matter, and for the long timescales necessary for stellar evolution and the development of life. This is not to suggest a dramatic act of design, but rather to highlight the profound, almost miraculous coherence of the physical laws themselves. They form a consistent, interconnected set that permits a universe of such richness and potential. The very possibility of our conscious minds asking these questions, of our ability to even conceive of a static universe, is a testament to the dynamic, law-abiding nature of the reality that produced us. The profound beauty of our actual universe, then, lies not in a fixed, eternal stillness, but in its continuous creation and transformation, all within the elegant framework of these unbreakable conservation laws. It is a cosmos that is perpetually alive, ever-changing, yet fundamentally ordered. The gentle swirl of a galaxy, the steady pulse of a distant star, the imperceptible dance of electrons within an atom, each is a quiet testament to the enduring power of motion and the laws that govern it. This is a universe that fosters not anxiety, but a deep, contemplative wonder, inviting us to find our own rhythm within its grand, ceaseless flow. Our fleeting existence is a precious moment within this vast, dynamic tapestry, a brief flicker of awareness that is itself a product of cosmic motion and change. We are intimately connected to this cosmic dance, made of stardust set in motion by the universe's earliest movements and continuously shaped by its ongoing dynamism. This profound connection offers a deep sense of belonging, a tranquil awareness that our individual story is but one small, beautiful thread in the magnificent, ever-unfolding narrative of the cosmos. It is a universe that, in its very essence, is a symphony of motion, carefully orchestrated by its conservation laws, creating a canvas for endless possibilities and vibrant rhythm. As we draw towards the culmination of our deep thought experiment, reflecting upon a universe stripped of its inherent spin and motion, we realize that this hypothetical stillness profoundly illuminates the vibrant reality that actually cradles us. The very impossibility of such a static cosmos, as suggested by the bedrock principles of physics, is not a limitation, but rather a testament to the elegant self-consistency and dynamic potential of our universe. It is a subtle, yet powerful reassurance that the fundamental theoretical constructs, but the essential conditions for evolution and the emergence of life itself. The absence of an external agent to halt the cosmos, as we previously discussed, reinforces the universe's nature as a self-contained system, governed by internal principles that ensure its continuous, ordered unfolding. This profound, active, dynamic essence. The ceaseless, subtle activity of quantum fields, even in the deepest vacuum, as explored in our last reflection, is a constant reminder that pure stillness is not the universe's natural state. Instead, it hums with a latent energy, a perpetual motion at its most fundamental level, giving rise to fleeting virtual particles and a constant, unobservable dance that underpins all interactions. This inherent dynamism, this cosmic restlessness, phenomena we observe from the smallest subatomic interactions to the grandest galactic structures. It is the very engine of becoming, the wellspring from which all novelty and complexity emerge. Without this foundational activity, the universe would be an inert, unchanging tableau, a realm of absolute actuality without the capacity for transformation or growth. The intricate interdependencies of physical laws become especially clear when we consider the alternative. A universe where linear momentum is not conserved would be chaotic, with objects randomly accelerating and decelerating without cause, making any form of stable structure or predictable trajectory impossible. A universe where energy is not conserved would be equally unpredictable, with energy spontaneously appearing or vanishing, rendering the very concept of cause and effect meaningless. And, as our primary focus, a universe where angular momentum is not conserved would see all rotating systems, from electrons to galaxies, either spinning out of control or grinding to an instantaneous halt, leading to the collapse of all organized matter. These laws are not arbitrary constraints. They are the enabling conditions for the universe's coherence and its capacity to sustain complex systems. They provide the stable framework within which the cosmic drama can unfold, allowing for billions of years of stellar evolution, planetary formation, and eventually the blossoming of conscious life. This consistent adherence to fundamental principles is what gives our universe its remarkable predictability and allows for the scientific method itself. The ability to observe, to hypothesize, to test, and to refine our understanding of the cosmos relies entirely on the assumption that the laws of physics are universal and unchanging. If these laws were to fluctuate or be arbitrarily broken, as implied by an uncaused cessation of spin and motion, then the very enterprise of science would be impossible. Our capacity to map the stars, to understand the forces that bind atoms, and to trace the universe's history back to its earliest moments is a direct consequence of this underlying order, and for our own intellectual journey within it. The philosophical implications of this thought experiment extend to our very perception of reality. We, as conscious beings, are products of a dynamic, evolving universe. Our brains are intricate networks of constantly firing neurons, generating electrical impulses that constitute our thoughts, memories, and emotions. This ceaseless electrochemical activity is a microcosm of the universe's larger dynamism. If all motion were to cease, the very mechanisms that allow for consciousness would also halt. There would be no flow of information, no processing of sensory input, no internal experience. The universe would exist in a state of gift of this. It is a quiet reminder that our awareness is not separate from the cosmic dance, but an integral part of its intricate choreography. Thus, this journey into the profound hypothetical of a universe without spin ultimately brings us back to a deeper appreciation for the reality we inhabit. Our universe, in its continuous ordered flux, is a tapestry of motion and change. The conservation laws, grand, comforting rhythm, has illuminated the profound beauty and indispensable nature of the conservation laws that govern our reality. As we approach the tranquil conclusion of this thought experiment, it becomes evident that the very impossibility of such a static cosmos is not a limitation of physics. The conservation of angular momentum, for instance, is not merely a quantitative rule. It is the silent architect of stability, a principle woven into the very fabric of existence that ensures the enduring coherence of cosmic structures. Consider for a moment the ubiquitous presence of rotational stability in our daily lives. A spinning top remains upright, defying gravity, only as long as it maintains its angular momentum. A bicycle, notoriously unstable when still, gains remarkable balance once its wheels begin to turn. These familiar examples, seemingly simple, are miniature reflections of a grand cosmic truth. The rotating planets, held in their intricate orbital paths around their stars, are stabilized by the very angular momentum they possess, generating a centrifugal effect that counteracts the relentless inward pull of gravity. Without this ceaseless inherent spin, their trajectories would cease to be stable ellipses, transforming instead into direct accelerating plunges towards their gravitational centers. The elegance here lies in the dynamic equilibrium, a constant motion that creates stability, a dance that prevents collapse. Extending this understanding to the grand cosmic scale, the spiral arms of galaxies, those majestic pinwheels of stars, gas, and dust, are themselves structured and maintained by the collective angular momentum of their billions of constituent stars. If this galactic rotation were to cease, the delicate balance between gravity and centrifugal force would be shattered. The flat disc-like structures would begin an inexorable process of condensation, stars and gas clouds spiraling inward towards the supermassive black holes at their cores, transforming the familiar elegant spirals into much denser, more spherical agglomerations. This would be a process of structural simplification, a cosmic homogenization, where the intricate, varied patterns of galactic morphology would give way to a more uniform, gravitationally dominant state. It would be a universe where the visual poetry of the night sky, with its diverse galactic forms, would be largely lost, replaced by a more monotonous, inward collapsing landscape. This quiet contemplation reveals how profoundly the presence of angular momentum shapes the aesthetic and structural richness of the cosmos, allowing for the emergence of such diverse and beautiful forms. The very concept of a universe without spin also challenges our understanding of the origins of structure. Modern cosmological models, based on extensive observational data, suggest that the initial minute quantum fluctuations in the early universe were stretched by a period of rapid expansion known as inflation. These tiny ripples then served as the seeds for the large-scale structure we observe today, growing into vast cosmic webs of galaxies and clusters. But the formation of individual galaxies and star systems from these initial seeds also critically depended on the presence and conservation of angular momentum. As primordial gas clouds collapsed under gravity, any slight initial rotation was greatly amplified, leading to the formation of spinning disks, the birthplaces of stars and planets. In a universe where angular momentum could not be conserved or was universally absent, these processes of structured formation would be fundamentally altered. The universe would struggle to move beyond a diffuse, amorphous state, lacking the very mechanism that allows for the localized condensation and organization of matter into the distinct, rotating entities we observe. This returns us to the profound insights of Emmy Noether, whose theorem elegantly links conservation laws to the symmetries of spacetime. The conservation of angular momentum principle, regardless of how we orient ourselves in space. If the universe were to cease all rotation, it would imply a fundamental breaking of this symmetry, or at least the establishment of a globally preferred orientation. Such a breaking of symmetry would not only affect angular momentum, but could ripple through the entire theoretical framework of physics, potentially impacting other symmetries and their corresponding conservation laws in ways we can only begin to imagine. It highlights the deep interconnected web of principles that form the invisible scaffolding of reality, where a change in one fundamental thread could unravel the entire cosmic tapestry. The consistent, predictable nature of these symmetries is what allows us to formulate universal laws, providing a stable foundation for our scientific understanding. Ultimately, this thought experiment serves as a profound meditation on the dynamic nature of existence itself. Our universe is not a static painting, but a living, breathing entity, constantly in motion, continuously evolving, and perpetually transforming. We, as conscious beings, are intimately woven into this dynamic tapestry. The very act of observing, of thinking, of feeling, relies on the ceaseless flow of energy and the intricate dance of particles within our own bodies. Our individual existence, a fleeting pattern of awareness, is a micro-reflection of the universe's grand, ongoing dynamism. Realm where the very conditions for life, for consciousness, for the intricate complexity we embody, would be absent. The vibrant reality that surrounds us, with its swirling galaxies, its orbiting planets, and its humming quantum fields, is a testament to the elegant dance of conservation laws. These laws ensure not just stability, but also the continuous potential for change and new forms of existence. They are the quiet, unwavering principles that orchestrate the grand symphony of the cosmos, allowing it to unfold in a magnificent, unending story. In this understanding, we find a deep sense of peace and belonging, knowing that our fleeting moments are part of something so vast, so dynamic, and so profoundly ordered. The universe, in its perpetual energetic flow, offers an unending source of wonder, inviting us to find tranquility in its enduring rhythm and in our own place within its magnificent, ceaseless dance. A quiet. Our profound journey into the hypothetical, paradoxically, deepened our appreciation for the dynamic, intricate reality that actually cradles us. The very unlikelihood of such a static cosmos, as revealed by the fundamental tenets of physics, is not a mere theoretical curiosity, but rather a powerful testament to the elegant self-consistency and boundless potential of our universe. It is a quiet, yet powerful reassurance that simply abstract rules, but the indispensable architects of cosmic order, permitting a continuous. The universe, in its very essence, is a testament to motion, a grand, unfolding narrative sustained by these unbreakable principles. Consider once more the subtle, ceaseless activity of the quantum fields. Even in the deepest reaches of what we perceive as empty space, far removed this represents a fundamental the void, stands in stark contrast to further refined by quantum field theory, conspicuously absent in a truly static state. This deep, quiet activity is not a chaotic frenzy, but a regulated, ordered process, a testament to the underlying laws. This foundational dynamism, meticulously so carefully explored, is the ultimate wellspring of all complexity and structure, the formation of planets, and ultimately, for life itself. Undifferentiated to emerge, continuously shaped by its fundamental rhythms and resilient system. The conservation laws ensure a profound cosmic stability simply disappear. It transforms, driving new processes and sustaining existing ones. Momentum isn't arbitrarily lost, it is meticulously transferred, maintaining the intricate balance of interactions between all constituent parts of the cosmos. These laws provide an unwavering, steadfast, and true, or arbitrary, but operates on principles that are both elegantly simple and profoundly. When we contemplate the fine-tuning of the universe, a concept often explored in both scientific and philosophical discussions, it extends beyond merely the specific numerical values of constants. It also encompasses the very validity and intricate, across all scales and conditions, utterly impossible. The universe's parameters and its governing principles, eventual external, internal, diversity. Our capacity for thought, for wonder, for understanding, is a direct, beautiful consequence of this cosmic dance. Ultimately, serves as a tranquil, yet powerful. It would be a silence so absolute that no thought could ever break it, a stillness so profound that no dream could ever stir within it. Yet the universe we inhabit is filled with the quiet hum of quantum fields, enduring. The intricate tapestry of our universe, far from the imagined stillness, thrives on a continuous energetic dance, a grand cosmic ballet orchestrated by the very conservation laws we have so meticulously explored. This dynamic reality, where nothing is truly static, stands as a profound counterpoint to our thought experiment, highlighting that motion is not merely a feature of existence, but its very essence, its ceaseless heartbeat. The fact that the universe maintains its angular momentum on local scales, that energy is perpetually conserved through transformations, and that linear momentum flows uninterruptedly through interactions, ensures a cosmic order that allows for both predictability and breathtaking complexity. It is within this framework of enduring laws that the grand narrative of celestial evolution and the delicate unfolding of life itself become possible. Consider the profound implications for the concept of information. In a truly static, non-spinning very notion of information would be rendered inert. Information at its core is tied to change, to differences, to the rearrangement of matter and energy. It is encoded in the patterns of light reaching our telescopes, in the magnetic fields of stars, in the genetic sequences of living organisms, and in the intricate neural connections of our brains. All these forms of information rely on dynamic processes for their creation, transmission, and interpretation. If light itself were frozen, unable to carry signals, if particles could not interact to form complex arrangements, then information could not be generated, stored, or accessed. The universe would be a vast, unreadable library, its countless volumes filled with static, inaccessible data, a profound silence where no knowledge could ever be exchanged or understood. This thought emphasizes that our capacity for knowledge, for learning, for the very act of scientific discovery, is intrinsically linked to the active, dynamic nature of the cosmos. Our minds, in their quest to understand the universe, are themselves vibrant, information processing systems, a living testament to the universe's ceaseless activity. The enduring consistency of these conservation laws, these fundamental symmetries of nature, is what allows for the emergence of life and, indeed, for consciousness. The universe, through its billions of years of evolution, has moved from a state of primordial simplicity to one of astonishing complexity, giving rise to stars, galaxies, planets, and ultimately, beings capable of contemplating their own existence. This trajectory of increasing complexity is not a random accident. It is the direct consequence of the universe operating under a stable set of physical laws. The conservation of energy ensures that the fuel within stars burns predictably, providing the long timescales needed for planetary formation and the slow, intricate development of biological systems. The conservation of angular momentum guarantees that these systems, once formed, maintain their structural integrity and dynamic stability, providing a safe harbor for life to flourish. Without these foundational principles, the delicate conditions required for life's emergence would be impossible to sustain, leading to a cosmos of transient, unstable forms, incapable of evolving into anything resembling ordered biology. This brings us to a deep, contemplative reflection on our own place within this cosmic ballet. We are not merely passive observers of this magnificent, dynamic universe. We are, in the most profound sense, an integral part of it. Every atom in our bodies, heavier than hydrogen, was forged in the hearts of ancient stars, hurled across the cosmos in spectacular supernovae, and eventually gathered together by gravity to form our solar system and our planet. These atoms, once part of a distant star, now dance within us, participating in the complex biochemical reactions that constitute life and thought. Our very consciousness, our ability to ponder the universe's grand mysteries, is an emergent property of these dynamic interactions, a fleeting yet exquisite pattern of energy and information. This profound connection means that when we gaze at the night sky, we are not looking at something separate from ourselves, but at an extension of our own cosmic heritage, a mirror reflecting the dynamic processes that brought us into being. The thought experiment of a non-spinning universe, while a departure from reality, serves as a powerful intellectual exercise, a method of negative proof. By imagining a universe where these core principles are absent or violated, elegant robustness of our actual, the very resilience of the universe, its capacity to endure and evolve, is rooted in these conservation laws. They are not fragile rules that could easily be broken, but robust principles that govern every interaction, every transformation, every movement across the vastness of space and time. This inherent stability, this cosmic reliability, is what makes the universe comprehensible to us, allowing us to uncover its secrets through observation and mathematical reasoning. Without this underlying order, our attempts to understand the cosmos would be futile, lost in a sea of unpredictable chaos. The fact that we can formulate theories, make predictions, and discover new phenomena is a testament to the deep-seated elegance of these laws. They provide a predictable stage upon which the universe's magnificent drama unfolds, ensuring that each act flows logically from the last, creating a coherent and continuously evolving story. This final reflection on the impossibility of a static universe thus serves to amplify our wonder at the actual dynamic reality we inhabit. It is a universe that not only exists, but thrives on motion, on change, on the ceaseless interplay of forces and matter. It is a universe that, through its very nature, invites us to participate in its grand dance, to explore its mysteries, and to find our own sense of belonging within its vastness. The quiet hum of cosmic activity, the gentle pull of gravity, the distant sparkle of rotating galaxies. These are the tranquil lullabies of a universe that is profoundly alive, constantly renewing itself, and eternally governed by laws that ensure its magnificent unfolding. This deep appreciation for the universe's dynamic balance, its intricate order, and its endless potential offers a profound sense of peace. We are not just in the universe, we are of it, a part of its grand, spinning, and endlessly fascinating story. And as these thoughts gently settle in your mind, may you find a deeper calm in the knowledge of this enduring cosmic dance. Our exploration into the hypothetical stillness of a non-spinning universe devoid of its ceaseless motion has, in its very contemplation, woven a deeper appreciation for the vibrant, dynamic reality that embraces us. We have glimpsed a cosmos where the absence of angular and linear momentum would unravel the intricate dance of galaxies, dissolve the stability of atoms, and perhaps even freeze the very flow of time and consciousness itself. Yet the profound impossibility of such a scenario within the framework of known physics is not a limitation, but a testament to the elegant resilience and intrinsic potential of our actual universe. May these deep thoughts about the universe's inherent motion and the steadfast conservation laws carry you now into a world of tranquil sleep. Remember that the cosmos is not a static canvas, but a grand, living symphony, perpetually in motion, continuously evolving, and endlessly transforming, all orchestrated by principles of profound beauty and unwavering consistency. Your own existence, a fleeting yet conscious pattern of energy and information, is an integral part of this magnificent ongoing dance. You are, in a very real sense, a product of this cosmic dynamism, formed from stardust set in motion billions of years ago and continuously shaped by the universe's enduring rhythm. Fall asleep with this feeling of serenity, knowing that the fundamental laws that govern the stars, the planets, and the very fabric of space-time boundless possibilities of existence. Good night.